Welcome, welcome, quiet traveler of the deep night. Welcome, stardust that has somehow learned to think about stardust. Lie down now. Let the weight of the day, all of it, fall away from your shoulders, your neck, the small of your back, your hands that have been holding so much. Let the ceiling above you dissolve. Let it become the dome of a sky unpolluted by light, unpolluted by hurry, unpolluted by the endless buzzing of the human world. You are not going to sleep. You are going to look up, not with your eyes, with your imagination. Because tonight, we are going to travel. We will travel from cave walls to the edge of the observable universe. We will travel from the first human who noticed that the stars repeat, night after night, year after year, century after century, to the machines we are building right now, at this very moment, to listen to the silent heartbeat of existence. This is a story about a telescope called Roman, but it is also a story about you, about why you, this temporary arrangement of atoms that used to be inside a star, are capable of wondering about the universe that made you. That loop, stardust wondering about the stars, is the most beautiful feedback loop in all of nature. It is the universe becoming aware of itself. It is the cosmos opening its eyes and saying, "Oh, I am here, and I am beautiful." So breathe in, slowly, hold it for a moment. Breathe out, let the world fall away. Let the noises of the city or the silence of the countryside become just a texture, just a blanket, just a soft hum beneath the words you are about to hear. And let us begin at the beginning. Not the beginning of the universe. We will get there. The beginning of us looking up. The first astronomers, carved in bone and stone, long before electricity, long before cities, long before writing, long before agriculture. Even there were fires, and around those fires, in every human group on every continent, there were necks craned upward. We know this because they left us messages. They left us their questions, carved into bone and stone. They left us their wonder, painted on cave walls that would outlast their languages, their cultures, their entire civilizations. Let us visit those first astronomers now, quietly, softly, as if we are walking beside them in the dark. The cave of Lascaux, a bull, a bird, and the Pleiades. In southwestern France, there is a cave called Lascaux. 17,000 years ago, plus or minus a few centuries, because we are dealing with the slow patience of archaeology. Someone went deep into that cave. They carried a lump of charcoal. They carried a stone lamp burning animal fat. They crawled through narrow passages, their shoulders scraping against the rock. And then, in a chamber where no sunlight ever reached, they stopped. They looked up at the blank stone wall, and they began to paint. They painted a magnificent bull, huge, powerful, with curved horns that seemed to move in the flickering lamplight. Near the bull, they painted a strange bird on a stick, like a totem or a sign. And above them both, above the bull and the bird, they painted a scattering of dots. For decades, for nearly a century, archaeologists called this scene a hunting scene. The bull was prey. The bird was a spear thrower, a tool for throwing spears farther and harder. The dots were either decoration or wounds on the bull's body. That was the story they told. Then, in the early 1990s, a French researcher named Dr. Chantal Jégué-Wolkiwiz took a different approach. She asked a question that seems obvious in retrospect. But obvious questions are often the ones we miss. She asked, what if those dots are not random? What if they are not wounds? What if they are not decoration? What if they map the night sky? She spent years studying the precession of the equinoxes, the slow 26,000-year wobble of Earth's axis that makes the stars appear to drift across the sky over thousands of years. She wrote computer programs to run the star positions backward in time. She rewound the sky to approximately 17,000 years ago. The last ice age, when mammoths still walked Europe, when the English Channel was a river valley, when sea levels were so low that you could walk from France to England, and when she looked at the positions of the stars on a spring morning 17,000 years ago, she saw something remarkable. The dots on the cave wall, the ones above the bull and the bird, aligned perfectly with the Pleiades. The Pleiades, the Seven Sisters, an open star cluster in the constellation Taurus, about 444 light-years from Earth, visible to the naked eye on every continent, known by every human culture that has ever looked up. The Greeks called them the seven daughters of Atlas and Pleione. The Japanese call them Subaru, which is why the car company has a logo with 6 stars, though the cluster has 7 if you have sharp eyes. The Australian Aboriginal people call them the Seven Sisters, and their songs about the cluster are among the oldest continuous stories in human history. Some linguists estimate they have been sung for at least 10,000 years, and now, here they were, painted on a cave wall in France, 17,000 years after someone dipped charcoal in animal fat and touched it to stone. 17,000 years ago, someone looked up at the sky, noticed a cluster of stars that marked a particular season, and said, "This matters. I must record this." They did not have writing, they did not have paper, they did not have numbers beyond the fingers on their hands, but they had the human mind, the same mind that you have right now, lying in your bed, listening to this voice, and they used that mind to carve the cosmos into culture. But Lascaux is not the only place. The same cave contains another panel, this one called the crossed bison. Between 2 bison facing each other, their heads bowed, their horns crossed like a doorway, there is another cluster of dots. Dr. Jacques Wolkiewicz ran the star positions backward again. That cluster matched the northern crown, Corona Borealis, a small semicircular constellation that looks like a crown or a dipper. So Lascaux is not a hunting diary. Lascaux is not a random collection of animal drawings. Lascaux is an observatory, a map of the night sky as it appeared to our ancestors at the end of the last ice age. 17,000 years before the Hubble Space Telescope, humans were already doing astronomy. They were not doing it with mathematics or metal tubes. They were doing it with their eyes, their memories, and their hands. The Koa Valley, Comet Halley's ancient portrait. Now let us cross the Pyrenees Mountains from France into Portugal. The Koa Valley. Here, the landscape is different. Not deep caves, but open rock faces along the riverbank, standing stones that catch the morning sun, and on those stones, carved into the surface with stone tools, are thousands of images. Horses, aurochs, the wild ancestors of modern cattle, goats, and among the animals, something different, a thin, curved line, a crescent moon, and below it, a line of small dots, arranged not in a cluster but in a stream, like droplets of water falling from a bowl. For years, archaeologists called this a fertility symbol, a catch-all term that archaeologists use when they do not know what something means. But in the 1990s, a team of astronomers looked at the Koa Valley carvings with fresh eyes. They asked, What if the dots are not water drops? What if they are not abstract symbols? What if they are stars? They measured the pattern of the dots, the distances between them, the curve of the stream, and they recognized that pattern. It is the path of Comet Halley. Comet Halley, the most famous comet in human history, returns to the inner solar system every 75 to 76 years. We know it from medieval records, from Babylonian clay tablets, from the Bayeux tapestry that depicts the Norman conquest of England in 1066. The comet appears in that tapestry as a flaming star, seen as an omen of great change. But the Koa Valley carving is much older. When the astronomers calculated the orbit of Comet Halley backward in time, accounting for the gravitational tugs of Jupiter and Saturn that slightly alter its path each time it comes close to the Sun, they found that approximately 15,000 years ago, the comet would have appeared in the sky exactly as carved on the rock. The crescent moon, a crescent moon that hung in the western sky at dusk. The stream of dots, the comet's tail, seen edge-on, stretching across the heavens. 15,000 years ago, someone looked up, saw a celestial wanderer with a glowing tail that moved against the fixed stars night after night, and said, "This is not ordinary. This is not like the sun or the moon. This is a visitor, and I must remember it." They did not have cameras. They did not have writing. They had stone and patience. And they carved a comet into rock that would outlast their language, their culture, their entire species' memory. That carving is still there today. You can go to the Koa Valley. It is a UNESCO World Heritage Site now, and stand before a rock that holds the memory of a comet that will not return until the year 2061. The same comet that William the Conqueror saw before he invaded England. The same comet that Mark Twain was born under and died under. He entered the world in 1835, when Halley was visible, and left it in 1910, when Halley returned. The same comet that, 75 years from now, will appear again. And someone, maybe your grandchildren or their children, will look up and see the same celestial wanderer that a prehistoric human carved into a rock 15,000 years ago. That is continuity. That is the thread that connects us to the first astronomers. Nabta Playa, the calendar before the pyramids. Let us go further south now, way south, southern Egypt. Today, the region called Nabta Playa is a hyper-arid desert. Sand, cracked mud flats, heat that kills within hours if you have no shade and no water. It is one of the driest places on Earth. But 9,000 to 7,000 years ago, 7 to 9,000 years before the present, it was a savanna. Seasonal lakes filled with water during the summer monsoon. Grasses growing tall enough to hide a human. Giraffes, elephants, antelope, gazelle, and the people who hunted them. Those people left behind something astonishing. They left behind a stone circle, not huge, about 12 feet in diameter, so you could stand in the middle and touch the stones on both sides if you stretched out your arms, but deliberately constructed, small standing stones, some brought from more than a mile away, arranged in a rough circle, and in the center, a larger stone, like a table. At one point, there were also stone alignments radiating outward from the circle, like spokes of a wheel or rays of a sun. In the 1990s, archaeologists led by Fred Wendorf and Romuald Shield excavated Nabta Playa. They mapped every stone, they measured every alignment, and they realized this stone circle is an astronomical observatory. The circle aligns with the summer solstice sunrise. On the longest day of the year, the day when the sun reaches its highest point in the sky before beginning its slow descent toward winter, the sun rises exactly over one of the stones. If you stood at the center of the circle on that morning, you would see the sun appear directly above that stone, but it gets even more precise. Some of the radiating alignments, the stone lines that point outward from the center, point not to the sun but to the stars. Specifically, they point to the rising positions of bright stars as they appeared 7,000 years ago. Sirius, the brightest star in the night sky, part of the constellation Canis Major, the great dog. Arcturus, a bright orange giant in the constellation Boötes, the herdsman. Alpha Centauri, the closest star system to our sun, just 4.3 light-years away. Though 7,000 years ago, its position in the sky was different because of precession, the slow wobble of Earth's axis. These are not random stars. These are the stars that would have appeared just before sunrise at the time of the summer solstice. The heliacal rising of stars that marked different seasons. The people of Nabta Playa were not just watching the sun, they were watching the stars. They were tracking the slow dance of the heavens, and they built the oldest known astronomical alignment in the world. Older than Stonehenge by about 2,000 years. Older than the pyramids of Giza by about 4,000 years. Stonehenge is impressive. The stones are much larger. The circle is much wider. But Stonehenge was built between 3000 and 2000 BC. Nabta Playa was built between 6200 and 5400 BC, thousands of years earlier. Why did they do it? Not for science as we know it, not for curiosity alone, for survival. The summer solstice marked the beginning of the annual flood of the Nile. The Nile is a magical river. It floods every summer, depositing rich silt on its banks, making the land incredibly fertile. But if you do not know when the flood is coming, you could lose everything. Your crops, your home, your livestock. If you plant too early, the flood might wash your seeds away. If you plant too late, the flood might recede before your crops have time to grow and ripen. So you need a calendar. You need a way to know with certainty when the longest day has arrived. And that means you need to watch the sun. You need to mark the spot on the horizon where the sun rises on that longest day. And then you need to make that spot permanent, with stones, with carvings, with a circle that your children and your grandchildren can use. That is what the people of Nabta Playa did. They built a stone calendar, not because they were obsessed with the sky, because they needed to eat. The first observatories were not built by philosophers. They were built by farmers and herders who needed to know when to plant and when to harvest. That is a humbling thought. The same human mind that would one day build the Roman space telescope, capable of seeing galaxies 13 billion light-years away, started with a circle of stones to predict a river flood. But that is how knowledge grows. Step by step, stone by stone, photon by photon. The Nebra sky disk, a Bronze Age universe. Now let us jump forward in time, not to the present, not yet, to the Bronze Age, 1600 years before the birth of Christ, 3600 years before the present. Central Germany, a hilltop called Mittelberg, the Middle Mountain. The area is wooded now, quiet, with a view of the surrounding valleys. But 3,600 years ago, it was a sacred site. Someone, a community, perhaps a chief or a priest, buried something on that hilltop. They buried a bronze disc, a flat circle of metal about a foot in diameter, 32 centimeters. blue-green with age because bronze turns green when it oxidizes. On that disk, inlaid with gold foil so thin that it would crumple if you touched it with a finger, were symbols. A crescent moon, curving across the lower edge, a full moon, or perhaps the sun, at the center, and scattered across the disk, dozens of small gold circles, stars. Among the stars, a distinct cluster, 7 dots grouped closely together, not random, not decoration. The Pleiades again. The same cluster painted on the cave wall at Lascaux, the same cluster carved into the stones of the Koa Valley, the same cluster that would appear on pottery, on jewelry, on temple walls for thousands of years across every civilization on Earth. The Nebra sky disk also has 2 golden arcs along the edges, one on the left, one on the right. These arcs are not decorative. One arc marks the angle between the sunrise points on the summer solstice and the winter solstice, the extreme ends of the sun's annual motion along the horizon. The other arc marks the sunset points on the same solstices, but on the opposite side of the sky. This is a precise astronomical instrument. If you stand on a flat horizon, say, the hilltop of Middelburg, and you watch the sun rise every morning for a year, you will notice that the sun does not rise in the same place every day. It moves along the horizon. At the summer solstice, it rises farthest to the north. At the winter solstice, it rises farthest to the south. The angle between those 2 extreme points is about 82 degrees at the latitude of central Germany. The gold arc on the Nebra sky disk subtends, that is, spans 82 degrees. Exactly. Whoever made this disk measured the motion of the sun over at least 1 full year, maybe many years, and recorded the result in gold on bronze. This is the oldest known concrete representation of the cosmos. Not just a map of stars, but a computational device for tracking the seasons. The Nebra sky disk is a calendar in metal. For the people who made it, the sky was not a painting. It was not a myth. It was a clock that told them when to plant, when to harvest, when to gather the community for rituals, when to prepare for the long dark of winter. And the Pleiades, the cluster that appears on the disk, were part of that clock. In the Bronze Age, as in many agricultural societies, the rising of the Pleiades just before sunrise in the spring marked the time to begin planting, and the setting of the Pleiades in the autumn marked the time to harvest. 7 stars, a small cluster, made the difference between a full belly and an empty one. That is why our ancestors watched the sky, not for beauty alone, though there is beauty, for survival. And that survival instinct, that need to know what happens next, is the same instinct that drives us to build telescopes like Roman. We still want to know what happens next. We just ask the question on a larger scale now. Not when should I plant, but what will the universe do in the next billion years? The Babylonians, the first predictive astronomers. Let us move now to the ancient Near East, Mesopotamia, the land between the Tigris and Euphrates rivers, present-day Iraq. The Babylonians, they were not the first to look at the sky. Everyone looked. They were not the first to record what they saw. The Egyptians and the Chinese were doing that at the same time. But the Babylonians were the first to do something revolutionary. They invented predictive astronomy. Let me explain what that means. Most ancient cultures watched the sky. They noticed patterns. The sun rises in the east and sets in the west. The moon goes through phases. New moon, crescent, half, full, then back again. The planet Venus appears as a morning star for a while, then disappears. then reappears as an evening star. These are observations, but prediction is different. Prediction means you do not just say Venus sometimes appears in the morning. Prediction means you say, on the 23rd day of the month of Nisan, in the 3rd year of the reign of King whatever his name is, Venus will rise in the morning at exactly 5:30 a.m., and it will be visible for 42 minutes before the sun rises. Prediction requires mathematics. Prediction requires records kept for decades or centuries so that you can see the cycles. Prediction requires a shift in thinking from what is happening now to what will happen next. The Babylonians made that shift. By the 8th century BC, 2,800 years ago, Babylonian scribes were recording the positions of planets every single night. They wrote on clay tablets in cuneiform script, wedge-shaped marks pressed into wet clay with a stylus, then baked hard in the sun. Hundreds of thousands of clay tablets survive in museums today. The British Museum in London, the Louvre in Paris, the Pergamon Museum in Berlin. Thousands of them contain astronomical observations. The scribes recorded the position of Jupiter against the background stars. They recorded the rising and setting times of Venus. They recorded eclipses of the sun and the moon, and the gaps between eclipses. They did this for generations. Fathers trained sons. Sons trained their sons. The tablets accumulated in archives, in temple libraries, in the royal palaces. And then, around the 4th century BC, 2,400 years ago, the Babylonians had enough data. They discovered something profound. Planetary motion is not random. It is periodic. It repeats. Venus follows the same pattern of morning and evening appearances every 8 years. Jupiter follows the same pattern of positions along the zodiac every 12 years. Saturn, the slowest of the visible planets, repeats its pattern every 30 years. These numbers are not exact. They are approximations, but they are close enough for prediction. The Babylonians developed mathematical methods to calculate where the planets would be on any given night, months, or even years in advance. They calculated the length of the lunar month, the time from one new moon to the next, to within seconds of the true value. They predicted solar and lunar eclipses. They even knew that solar eclipses are not visible everywhere on Earth. That a prediction of a solar eclipse was a prediction that somewhere on Earth, the moon would pass between the sun and a particular observer. This is remarkable. They did all of this without telescopes, without calculus, without algebra as we know it, without even the concept of zero as a number. Zero was not introduced to the West until much later by the Indian mathematicians and then through the Arab world. The Babylonians used base 60 arithmetic, which is why we still have 60 seconds in a minute and 60 minutes in an hour. And they used their base 60 system to predict the sky. The Greek astronomer Hipparchus, in the 2nd century BC, used Babylonian data to develop his own models. Claudius Ptolemy, in the 2nd century AD, used Babylonian data to write the Almagest, the most influential astronomy textbook in history, used for 1,400 years. The Babylonians were the first true scientists of the sky. They did not ask why the planets move. They asked how they move, and they answered with numbers. That is also what Roman will do. Roman will not ask what is dark energy, not directly. Roman will ask, how do galaxies cluster? How do supernovae appear at different distances? How does the weak lensing signal change with cosmic time? And from the measurements, the cold, precise, numerical measurements, the what will emerge. Just as the Babylonians' tables of planetary positions led eventually to Newton's theory of gravity, Romans' tables of galaxy shapes and supernova distances will lead, someday, by someone, to a theory of dark energy, or so we hope. Ancient China, guest stars and comets. On the other side of the world, far from Babylon, far from Egypt, far from the stone circles of Europe, another civilization was watching the sky with equal dedication. Ancient China. Chinese astronomy dates back at least 4,000 years, probably more. But the earliest written records come from the Shang dynasty. Around 1600 BC, the Chinese did something different from the Babylonians. The Babylonians were interested in prediction, in calculating future positions. The Chinese were interested in omens. For the Chinese emperor, the sky was a direct message from heaven. The emperor was the son of heaven, ruling by the mandate of heaven. If he ruled well, the sky would be calm, predictable, orderly, harmonious. If he ruled poorly, the sky would send warnings. A guest star, a new star appearing where none had been before, that was a warning. A broom star, a comet, that was a warning. A broken rainbow, a meteor or a meteor shower, that was a warning. An eclipse, a terrifying event in which the sun or moon seemed to be eaten, that was a serious warning, often interpreted as a threat to the emperor's life. So the emperor appointed court astronomers. Their job was to watch the sky every single night, without fail, and to report anything unusual. If they missed something important, if a comet appeared and they did not see it, or if they saw it but did not record it accurately, they could be executed. This produced a powerful incentive to be thorough. For more than 2,000 years, from the Han Dynasty, around 200, through the Qing Dynasty, the early 1900s, Chinese court astronomers kept continuous records of the sky. They recorded the positions of planets. They recorded eclipses. They recorded sunspots, dark blemishes on the sun that are invisible without a telescope, but can be seen if the sun is low on the horizon and obscured by haze or cloud. And they recorded guest stars. The most famous guest star appeared in the summer of the year 1054. Chinese astronomers in the Song Dynasty recorded a star in the constellation Taurus, the bull, that was so bright it could be seen in daylight, for 23 days. It remained visible in the night sky for nearly 2 years, slowly fading. This guest star was a supernova, the explosion of a massive star at the end of its life. Today, we call the remnant of that explosion the Crab Nebula. It is located about 6,500 light-years from Earth, in the constellation Taurus, exactly where the Chinese astronomers saw the guest star. The Crab Nebula is still expanding. It is still glowing. It is one of the most studied objects in the night sky. We have photographed it in visible light, in infrared, in X-rays, and in radio waves. We have seen the pulsar at its center, a neutron star spinning 30 times per second, emitting beams of radiation like a cosmic lighthouse. And we know, from the Chinese records, exactly when the star exploded. The year 1054, the summer, not about 1,000 years ago, the exact year. That is the power of historical astronomy. But the Chinese records do more than just date the Crab Nebula. They also preserve the careful, systematic observation of the sky over centuries. In the 1950s and 1960s, the English astronomer Joseph Needham compiled the monumental work Science and Civilization in China. He translated thousands of Chinese astronomical records. He found observations of comets that helped Edmund Halley in the 1700s calculate the orbit of his comet. He found observations of sunspots that helped modern scientists understand the sun's long-term behavior. He found records of guest stars that might be other supernovae, waiting to be identified in the remnants of old explosions. The Chinese astronomers did not know what a supernova was. They had no concept of nuclear fusion, no idea that stars are powered by converting hydrogen into helium. They thought they were seeing heaven's warning, but their records, their careful, daily, dutiful records, have become a gift to modern science. That is another theme that runs through the history of astronomy. You do not have to understand what you are seeing. You just have to see it. You just have to record it. Because someday, decades later, centuries later, millennia later, someone with a better understanding will look at your records and see something you could not have imagined. Roman will produce 20 petabytes of data, 20 million gigabytes. That is about 2,000 times the entire text content of the United States Library of Congress. Every hour. No one person, no team of people will read all of that data. Much of it will sit on servers, untouched for years. But someday, some graduate student, probably not born yet, will download a patch of Roman data that no one has ever looked at. And in that data, they will see something. A galaxy that should not exist. A supernova that exploded at the wrong time. A pattern of weak lensing that does not fit the standard model. And they will say, "That's strange." And that strangeness will be the beginning of a new discovery. Just as the strangeness of a guest star in 1054 led to the Crab Nebula. Just as the strangeness of flat rotation curves led to dark matter. Just as the strangeness of faint supernovae led to dark energy. Strangeness is the engine of discovery, and Roman will produce strangeness in abundance. The Maya, tracking Venus, across the centuries. Let us cross the Pacific now, from China to Central America. The Maya civilization. They built their cities in the jungles of what is now Mexico, Guatemala, Belize, Honduras, and El Salvador. Their classical period, the time of the great cities like Tikal, Palenque, Copan, was from about 250 AD to 900 AD, but their astronomical traditions go back much further, possibly to the Olmecs, the earlier civilization that influenced them. The Maya were obsessed with time. They had not one calendar but three. The Tzolkin, a 260-day sacred calendar used for religious ceremonies. The Hab, a 365-day solar calendar used for agriculture. The Long Count, a linear calendar that counted days from a mythical starting point in the distant past, equivalent to August 11th, 3114 B.C. in our calendar. The Long Count is famous because one of its cycles ended on December 21st, 2012, which led to nonsense about the end of the world. But the Maya did not think the world would end. They thought a cycle would end, and a new cycle would begin, like the odometer on a car rolling over from 99,999 to zero. But let us focus on the Maya and the sky. They built observatories. The most famous is El Caracol, the snail, at the great city of Chichen Itza. El Caracol is a round tower with windows placed at specific angles. If you stand inside and look through the windows on certain dates, you will see the planet Venus at its extreme positions on the horizon. Venus was the most important celestial body for the Maya, more important than the sun or the moon, according to some scholars. Why? Because Venus is bright, because Venus moves in a striking pattern, appearing as a morning star for about 263 days, then disappearing for about 50 days, then appearing as an evening star for about 263 days, then disappearing again before repeating the cycle. The entire cycle, from one morning star appearance to the next, takes 584 days. The Maya measured that cycle. They measured it precisely. They recorded the positions of Venus in the Dresden Codex, a bark paper book that survived the Spanish conquest, one of only 4 Maya codices known to exist. The Dresden Codex contains Venus tables, pages of calculations showing where Venus will appear in the sky for years in advance. The calculations are accurate to within 1 day in 600 years. That is better than the astronomical tables of the ancient Greeks, better than the tables of the early medieval Europeans. How did the Maya do it? They did not have telescopes. They did not have the mathematical notation that we use. No decimals, no fractions, no algebra in the modern sense. They had base 20 arithmetic, using fingers and toes, combined with an incredible dedication to observing the same planet, night after night, year after year, generation after generation. They noticed that 8 cycles of Venus, 8 times 584 days, equals 5 cycles of the Tzolk'in calendar, 5 times 260 days, approximately. Not exactly, but close enough that they could correct the small error over longer periods. They also noticed that 13 cycles of Venus, 13 times 584, equals 10 cycles of the Hobbes solar calendar, 10 times 365. Again, approximately. These are not coincidences. These are mathematical relationships discovered by humans who spent their lives watching the sky. The Maya used their Venus tables to schedule wars and human sacrifices. Serious scholars debate this, but the consensus is that the Maya timed their military campaigns to coincide with the first morning appearance of Venus, which they associated with war. They also used the tables for agriculture, for religious ceremonies, for the timing of royal accessions. But here is what is beautiful about the Maya. They did not need to do any of this. They could have planted their crops when the rain came, fought their wars when the season favored movement, held their ceremonies when the priests felt the time was right. But they chose to tie everything to the sky. They chose to measure. They chose to calculate. They chose to build a civilization based on the positions of a planet that is, from Earth, just a bright dot of light. Why? Because the sky is predictable. The sky is reliable. The sky is the one thing that does not lie. If you know the sky, you know when to act. That is still true today. We do not time our wars to Venus, but we time our rocket launches to planetary alignments, using the gravity of Jupiter to slingshot probes to Saturn, using the orbital mechanics of Mars to plan a human landing. We do not sacrifice prisoners on altars when Venus rises, but we wake up at 4 a.m. to point the Roman space telescope at a particular patch of sky because we know, from calculations based on centuries of astronomy, that at that exact moment, a distant galaxy will be perfectly positioned for weak lensing measurement. The Maya would understand that. They would not understand the technology, the coronagraphs, the deformable mirrors, the mercury-cadmium telluride detectors. But they would understand the impulse, the need to know, the desire to put your trust in the order of the cosmos. The Greeks, from spheres to systems. We cannot leave the ancient world without pausing on the Greeks. Not because they were smarter than everyone else. They were not. Every civilization had brilliant minds, but the Greeks wrote down their arguments. They left us not just observations, but reasoning. They told us why they thought what they thought, which means we can argue with them, test their ideas, and build on their mistakes. That is the essence of science. Thales of Miletus, around the year 600 BC, is said to have predicted a solar eclipse. The story goes that he saw the sun go dark in the middle of the day, just when he had calculated it would. Historians doubt the details, but the story matters because it represents a shift. Before Thales, eclipses were omens from angry gods. After Thales, eclipses were natural events that could be predicted if you paid close enough attention. Thales also proposed that the Earth floats on water, which is wrong, but it is a physical explanation, not a myth. He asked, "What is the world made of?" and answered water. Wrong again. But the question itself was revolutionary. That seems obvious to us. But for most of human history, people thought the bright star in the morning was different from the bright star in the evening. The Pythagoreans realized the same planet moves from one side of the sun to the other. Eratosthenes, around 240 BC, measured the circumference of the Earth. He had heard that in the city of Syene, now Aswan, in southern Egypt, the sun shone directly down a well at noon on the summer solstice, meaning the sun was exactly overhead. He knew that in Alexandria, where he lived, the sun never got that high. At noon on the summer solstice, the sun was about 7.2 degrees away from the zenith, 1/50th of a full circle. If you assume that the sun is so far away that its rays are parallel when they reach Earth, a big assumption, but correct, then the distance between Syene and Alexandria must be 1/50th of the circumference of the Earth. He measured the distance, about 500 miles. Multiply by 50, 25,000 miles. The true circumference is about 24,900 miles. He was off by less than 1%. That is astonishing. He did it with a stick, a well, a camel, or rather, the distance a camel could walk in a certain number of days. And geometry. Hipparchus, around 150 BC, compiled the first comprehensive star catalog. He listed about 850 stars, some sources say 1,022. With their positions and their brightnesses, he invented the magnitude system. The brightest stars are magnitude 1. The faintest visible to the naked eye are magnitude 6. We still use a version of that system today. With modern telescopes, we can see stars down to magnitude 30, a billion times fainter than the naked eye limit. Hipparchus also discovered precession, the slow wobble of Earth's axis that makes the stars drift over thousands of years. He noticed that the position of the star Spica had changed relative to the autumnal equinox compared to earlier Babylonian records. He did not know why, but he measured the change, and that measurement became the foundation for understanding that the Earth is not a fixed reference point in space. Everything moves. Claudius Ptolemy, around 150 AD, wrote the Almagest. The name comes from the Arabic Al-Majisti, meaning the greatest. It was a 13-book synthesis of everything known about the sky. It contained the star catalog of Hipparchus, updated. It contained a geometric model of the solar system, with Earth at the center, geocentric. Planets moved on small circles called epicycles, whose centers moved on larger circles called deferents. It was complicated, but it worked. It predicted planetary positions well enough for navigation, for astrology, for calendar keeping. It lasted 1,400 years. No scientific model has lasted that long since. Copernicus, in the 1500s, proposed a heliocentric model, sun at the center. That was simpler, but initially, no more accurate. Galileo, in the 1600s, used a telescope to gather evidence that convinced people that the Earth moves. But Ptolemy's model was not stupid. It was a reasonable interpretation of the data available, without telescopes, without parallax measurements, without the physics of Newton. Ptolemy did what all scientists do. He looked at the data. He built a model that fit the data. He made predictions. When the predictions failed, he adjusted the model. That is the scientific method. We do the same thing today. We have a model, the standard model of cosmology, that includes dark matter and dark energy, and a bang at the beginning. It fits the data remarkably well, but it has gaps. Dark matter has not been directly detected. Dark energy remains a name for our ignorance. The Hubble constant, the rate of expansion, measured by different methods, gives slightly different answers. These discrepancies are the epicycles of our time. They tell us that our model is not complete. Roman will measure those discrepancies with far greater precision than we have today. And then, perhaps, a new Copernicus, a new Einstein, will look at Roman's data and see a simpler, deeper explanation. That is the hope. That is why we build. Part 2. The birth of a new I. Who was Nancy Grace Roman? Before we go further into the science, into dark matter and dark energy and weak lensing, let us meet the telescope's namesake. Because names matter. They are not just labels. They are stories. They are promises. The Nancy Grace Roman Space Telescope was not always called that. It started as the Wide Field Infrared Survey Telescope, WFIRST, pronounced W first. That is a functional name. It describes what the telescope does. A wide field, in infrared, doing a survey. But in 2020, NASA announced that the mission would be renamed. It would be named after the woman who made space-based astronomy possible. The woman they called the mother of Hubble, Nancy Grace Roman. Let me tell you her story. Childhood. A 4-year-old asks the right question. Nancy Grace Roman was born on May 16, 1925, in Nashville, Tennessee. Her father was a geophysicist, a scientist who studied the Earth. Her mother was a teacher and a music lover. The family moved often because of her father's work, from Nashville to Houston to New Jersey to Oklahoma. Wherever they went, Nancy looked at the sky. When she was 4 years old, she was standing outside with her mother one evening. She looked up. Just as you are looking up now, or imagining looking up. And she pointed. "What is that?" she asked. Her mother said, "Those are stars." Nancy asked, "What are stars?" Her mother, perhaps tired of questions, or perhaps simply answering honestly, said, "They are like the sun, only much farther away." And Nancy Grace Roman, 4 years old, thought about that. If they are like the sun, then they must be hot. If they are hot, they must be burning. If they are burning, they must have fuel. If they have fuel, they must eventually run out. And if they run out, they must change or die. But also, if they are like the sun, they might have planets, and if they have planets, those planets might have conditions suitable for life. And if those planets have life, some of that life might be intelligent. And if some of that life is intelligent, they might be looking back at us. All of that passed through the mind of a 4-year-old girl. She never forgot that moment. She later said, "From that time on, I knew I wanted to study astronomy." She wanted to know what stars are, not just their names, their nature, the path of resistance. In the 1930s and 1940s, astronomy was almost entirely male. Women could be computers, calculators, at observatories. Harvard, in the early 1900s, employed a group of women who analyzed photographic plates and classified stars. They were called the Harvard computers. They made major discoveries. Annie Jump Cannon developed the stellar classification system we still use today. Henrietta Swan Leavitt discovered the period luminosity relation for Cepheid variable stars, the relation that allowed Edwin Hubble to measure the distance to Andromeda. Cecilia Payne-Gaposchkin showed that stars are made mostly of hydrogen and helium, but they were not allowed to use the telescopes at Harvard. They were not allowed to be observers. The telescopes were considered too dangerous for women, too cold, too demanding. And that was Harvard, one of the more progressive institutions. Nancy Grace Roman encountered the same barriers. She applied to Swarthmore College, a small liberal arts college near Philadelphia. She wanted to major in astronomy. A faculty advisor told her, she ignored him. She got her bachelor's degree in 1946. She applied to graduate schools. Princeton had a strong astronomy program, but Princeton did not admit women to graduate school in astronomy until 1975. She was rejected, not because she was not qualified, but because she was a woman. She went to the University of Chicago instead. The University of Chicago had a world-class astronomy department. It also had the Yerkes Observatory, a magnificent old telescope in Williams Bay, Wisconsin, with a 40-inch refractor that was one of the largest in the world when it was built in the 1890s. Roman did her PhD work at Yerkes. She studied the distribution of stars in the Milky Way, a laborious process involving photographic plates, manual measurements, and endless calculations by hand. She found that stars are not randomly distributed. They cluster in spiral arms. That seems obvious today. We have maps of the Milky Way showing its spiral structure, but in the 1940s and early 1950s, that structure was not confirmed. Roman's work helped confirm it. She also identified the different stellar populations in the galaxy: the thin disk, the thick disk, the halo. That classification is still used. She got her PhD in 1949. She stayed at the University of Chicago as a research associate for several years. She got a job at the Naval Research Laboratory in Washington, D.C., studying radio astronomy, a new field at the time. But she wanted to do something bigger. She wanted to see the sky from above the atmosphere. The mother of Hubble. In 1959, Nancy Grace Roman moved to a new organization. It was called the National Aeronautics and Space Administration, NASA. NASA had been created in 1958 in response to the Soviet Union's launch of Sputnik, the first artificial satellite. At first, NASA was focused on rockets, on satellites, on sending humans into space. But the agency also had a small astronomy program. Roman became the chief of astronomy and relativity at NASA's headquarters in Washington, D.C. She was the first woman to hold an executive position at NASA. She was 34 years old. Her task: convince astronomers that space telescopes were worth building. Astronomers were skeptical. Why put a telescope in space? It is expensive. The launch could fail. If it breaks, you cannot fix it, or so they thought. Hubble would later prove that space telescopes can be repaired, but that was not clear in 1960. On the ground, you can build a telescope much larger for the same money. The telescopes on Mount Palomar and Mount Wilson, the 200-inch Hale telescope, the 100-inch Hooker, were doing fine. Why risk space? Roman did not argue. She showed. She organized meetings. She invited astronomers to NASA headquarters to discuss the potential of space-based astronomy. She wrote reports, dozens of reports, laying out the scientific case. She argued, from above the atmosphere, you can see ultraviolet light, blocked by ozone. You can see infrared light, blocked by water vapor and carbon dioxide. You do not have atmospheric blur, the twinkling that ruins fine detail. You can stare at the same patch of sky for days, because there is no day-night cycle in space. You can measure the positions of stars with far greater precision, because you do not have the atmosphere bending the light. She gave the proposed telescope a name, the Large Space Telescope. Later, it would be renamed the Hubble Space Telescope, after Edwin Hubble, who discovered the expansion of the universe. The project was nearly canceled multiple times. Budgets were cut. The space shuttle, needed to launch the telescope and to service it, suffered delays and disasters. The Challenger explosion in 1986 put all NASA missions on hold for 2 years. But Roman did not give up. She lobbied Congress. She testified at hearings. She explained to senators and congressmen, many of whom had no science background, why the nation should spend billions of dollars on a telescope. She told them, "We will discover things we cannot imagine." That is a hard argument to make. It is also the only honest argument for basic research. You do not know what you will find. That is why you look. The telescope finally launched in 1990. Nancy Grace Roman was 65 years old. She had retired from NASA in 1979, 10 years before the launch. She watched the launch from Florida. She watched the deployment. She watched the first images. Blurry, flawed, because the mirror was ground to the wrong shape. She felt terrible, but she also knew this could be fixed, and it was. In 1993, astronauts installed corrective optics. Hubble saw clearly the images that came down, the Eagle Nebula, the Hubble Deep Field, the Ultra Deep Field, transformed astronomy. Nancy Grace Roman never claimed credit. She always said, it was a team effort. Thousands of people worked on Hubble. I just started the conversation. When she died in 2018, at the age of 93, the astronomy community mourned. Then NASA announced, the next great space telescope, the Wide Field Infrared Survey Telescope, would be renamed. It would be called the Nancy Grace Roman Space Telescope because she was the silent architect of space-based astronomy. She built the political and scientific foundation for everything that followed. Hubble, Chandra, Spitzer, Webb, and now Roman. Tonight, we say her name softly. Nancy Grace Roman, thank you for starting the conversation. The Invisible 95%. A detailed history of surprise. Now we come to the deepest mystery, the reason Roman exists, the reason we are telling this story. 95% of the universe is unknown. Let that number sit with you for a moment. 95%. If the universe were $100, we can account for $5. The other $95 are invisible to every instrument we have ever built, except in one way: gravity. We know dark matter and dark energy exist because of their gravitational effects. But in every other way, light, sound, touch, smell, taste, they are silent. They do not interact with our world. They are not just hiding in a dark corner of the room. They are not just far away. They are not just dim. They are fundamentally different from the stuff we are made of. And for a century, we have been trying to figure out what they are. Let me walk you through that century, slowly, one clue at a time. The first clue: Fritz Zwicky and the Coma Cluster. The year: 1933. The place: California Institute of Technology, Caltech, in Pasadena, California. The person: Fritz Zwicky. Zwicky was Swiss. He was educated at the Swiss Federal Institute of Technology in Zurich, the same school where Albert Einstein studied. He moved to the United States in 1925 to work at Caltech. Zwicky had a temper. He once called his colleagues spherical bastards because, he said, they were bastards no matter which way you looked at them. He was also brilliant. He and his colleague Walter Beatty, a German astronomer, coined the term supernova to describe the explosion of a star. They correctly hypothesized that supernovae could produce neutron stars, the ultra-dense remnants of collapsed stellar cores. They also speculated that supernovae might create cosmic rays, high-energy particles that bombard Earth from space. They were right about both, but Zwicky's most profound insight came from looking at the Coma Cluster. The Coma Cluster is a swarm of galaxies in the constellation Coma Berenices, Berenice's Hare. It is about 320 million light-years away. It contains more than 1,000 galaxies, maybe 2,000. Counting them is difficult because they are faint and crowded. Zwicky measured the speed at which those galaxies orbit the center of the cluster. He used the virial theorem, a mathematical relationship that connects the kinetic energy of moving objects to the gravitational potential holding them together. The virial theorem says, if you measure the speed of objects in a cluster, you can calculate the total mass of the cluster, even if most of that mass is invisible. Zwicky did the calculation. He got a number, about 450 times the mass of the Sun for each galaxy. That is a lot of mass. Then he added up the visible mass, the stars in the galaxies, the hot gas between the galaxies. The visible mass was about 1% of the mass he calculated. 1%. He wrote a paper in the journal Helvetica Physica Acta, a Swiss physics journal. He proposed that there was dunkle materie, dark matter. That was gravitationally active but emitted no light. The paper was ignored, partly because 1933 was the Great Depression. No one had money to spend on invisible matter, partly because Zwicky was an outsider. He was Swiss. He had a temper. He was not part of the establishment, partly because the idea seemed absurd. Invisible matter holding clusters together, but mostly because it was 30 years ahead of its time. Vera Rubin and the flat rotation curves. 30 years later, a new astronomer took up the problem. She did not set out to find dark matter. She set out to understand how galaxies rotate, and in doing so, she found evidence that dark matter is everywhere. Her name was Vera Rubin. Vera Rubin was born in 1928 in Philadelphia. She made her first telescope at 14, a cardboard tube with a lens she ground herself. She was the only astronomy major at Vassar College. She applied to Princeton for graduate school, the same Princeton that rejected Nancy Grace Roman for the same reason. Princeton did not admit women to its graduate astronomy program until 1975. Rubin was rejected. She went to Cornell University for a master's degree. She studied with Hans Bethe and Richard Feynman, both future Nobel laureates. She then transferred to Georgetown University for her PhD because she could do that while her husband worked in Washington. Her PhD thesis argued that galaxies are not randomly distributed. They cluster. She was right, but she could not get a research position. She was a woman, so she taught at Georgetown, at the University of Maryland. In the 1960s, she began working with a colleague named Kent Ford. Ford had built a sensitive spectrograph, an instrument that spreads light into its component wavelengths, using an image tube, a new technology that amplified light electronically. Together, they pointed their spectrograph at the Andromeda galaxy. Andromeda is our nearest large spiral neighbor, 2.5 million light-years away. It is similar in size to the Milky Way. Rubin and Ford wanted to measure how fast Andromeda rotates at different distances from its center. Standard physics, Newton's laws, Kepler's laws, predicted that stars farther from the center should move slower. That is how the solar system works. Mercury orbits the sun in 88 days. Neptune takes 165 years. The farther you are from the center of mass, the slower you orbit. That is gravity. Rubin and Ford measured the rotation speed of Andromeda near its center. It was fast, about 220 kilometers per second. They measured it halfway out, about 50,000 light-years from the center. It was still fast, about 220 kilometers per second. They measured it near the edge, at the visible edge of the galaxy, where the spiral arms fade into darkness. It was still fast, 220 kilometers per second. That should be impossible. At that distance, with only the visible mass, the orbital speed should be much lower, maybe 100 kilometers per second. Something was holding those outer stars, something invisible, something with mass. Rubin and Ford published their results in 1970. They measured 50 more galaxies, same flat rotation curves, galaxy after galaxy. By the late 1970s, the evidence was overwhelming. Dark matter was not a fluke of one cluster. It was a universal property of galaxies. Rubin became famous as an astronomer can be without winning the Nobel Prize, which she did not win, though many argue she should have. She was elected to the National Academy of Sciences. She received the National Medal of Science. She continued to work until her death in 2016. She was 88 years old. In her later years, she was often asked, "What is dark matter?" She would smile and say, "I don't know." That's why we need more telescopes. The missing mass problem. Putting numbers on our ignorance. Let me put the numbers in a way that you can hold in your mind. The Milky Way galaxy, our home, is about 100,000 light-years across. We live about 26,000 light-years from the center. The sun orbits the galactic center at about 220 kilometers per second. That is about 490,000 miles per hour. At that speed, it takes the sun about 250 million years to complete one orbit. The last time the sun was on this side of the galaxy, the dinosaurs were still alive, though barely. The Cretaceous period was ending. and the Paleogene period was beginning. From the sun's orbital speed and distance, we can calculate the mass inside the sun's orbit. That mass is about 100 billion times the mass of the sun. That is a lot of mass, but it includes the stars, the gas, the dust, and the dark matter inside that radius. Now consider the outer parts of the Milky Way. Beyond the sun's orbit, out to the edge of the galaxy, the rotation speed does not slow down. That means there must be additional mass outside the sun's orbit. In the halo of the galaxy. How much additional mass? About 1.5 trillion times the mass of the sun, 10 times more than the visible mass. The Milky Way is mostly dark. All galaxies are mostly dark. The ratio varies from galaxy to galaxy. Some have more dark matter, some have less. But on average, in the universe as a whole, dark matter outnumbers normal matter by about 5 to 1. 5 to 1. That means if you took all the normal matter in the universe, every star, every planet, every gas cloud, every dust grain, every mouse, every human, every whale, every spider, every bacterium, you would have about 17% of the mass you need to account for the gravity we observe. The other 83% is dark matter. And on top of that, dark energy makes up an even larger share of the universe's energy budget. But we will get to dark energy soon. First, let us explore the candidates for dark matter. The guesses, the hopes, the almost certainly wrongs, and the maybe, just maybe rights. The candidate zoo. What dark matter might be. We do not know what dark matter is, but we have many guesses. Each guess tells a different story about the universe. Each guess has different implications for the future of physics. Let me walk you through the most prominent candidates. Think of them as characters in a mystery novel. Each one looks suspicious. Only one, maybe none, is the real culprit. Candidate 1, MACHOs. MACHO stands for Massive Compact Halo Object. These are normal matter objects, but dark, not because they are made of exotic particles, but because they do not shine. Examples: black holes, neutron stars, brown dwarfs, free-floating planets. Black holes are dark because their gravity is so strong that even light cannot escape. Neutron stars are dark because they are tiny, only about 10 kilometers across, and have cooled down after their formation. Brown dwarfs are failed stars. They are larger than planets but not massive enough to start nuclear fusion in their cores. They glow faintly in infrared, but very faintly. Free-floating planets are planets that were ejected from their star systems. They have no star to illuminate them. In the 1990s, two teams, the MACHO collaboration and the Eros collaboration, searched for MACHOs using gravitational microlensing. Microlensing is a beautiful phenomenon. When a massive object passes between us and a distant star, its gravity bends and magnifies the star's light. The star appears to brighten over days or weeks, then fade back to normal. The pattern of brightening tells you the mass of the object. The MACHO and Eros teams found some microlensing events. They found enough to say, MACHOs exist, but not enough to account for all of dark matter. The number of MACHOs in the galactic halo can account for at most 20% of the dark matter, probably less. Most dark matter is not MACHOs. Candidate 2, WIMPs. WIMP stands for Weakly Interacting Massive Particle. This is the most popular candidate among physicists. For a long time, it was the leading hypothesis. WIMPs would be particles like neutrinos, but much heavier. Neutrinos are incredibly light. A neutrino has a mass less than 1/millionth the mass of an electron. WIMPs would be much heavier, maybe 10 to 1,000 times the mass of a proton. WIMPs would interact through the weak nuclear force and gravity, but not through electromagnetism or the strong nuclear force. That means they would not emit or absorb light. They would rarely collide with normal matter, but rarely does not mean never. If dark matter is made of WIMPs, then trillions of WIMPs are passing through your body every second, right now. As you lie there listening to this voice, they come from space, from the halo of the Milky Way, and they fly through you, through the ground, through the earth, without stopping. Most of them go right through you, because the weak interaction is, as the name says, weak. But once in a while, once in a very great while, a WIMP will actually bump into an atomic nucleus in your body. That bump would deposit a tiny amount of energy, a few thousandths of an electron volt, which is far too small for you to feel, but it is not too small for a sensitive detector. Experiments like Xenon NT in Italy, Lux Zeppelin in South Dakota, and Panda X in China have built enormous tanks of liquid xenon, a noble gas, heavy and transparent. Xenon is a good target because it has heavy nuclei. The heavier the nucleus, the bigger the bump. The tanks are buried deep underground, in mines, under mountains, to shield them from cosmic rays and other background radiation. Cosmic rays would produce false signals. They would look like WIMP collisions, even if no WIMP existed. The tanks are cooled to very low temperatures. They are surrounded by water, hundreds of thousands of gallons, to absorb neutrons from the surrounding rock. They are incredibly clean, cleaner than almost anything on Earth. The inner surfaces are polished to remove any trace of radioactive isotopes. Then they wait and watch and wait. As of 2026, zero. No unambiguous WIMP detection. The experiments have ruled out WIMPs at certain masses and certain interaction strengths, but they have not ruled out all WIMPs. The search continues. The current generation of experiments is about 1,000 times more sensitive than the first generation. The next generation, called Darwin, for dark matter, WIMP, search with liquid xenon, will be even larger. If WIMPs exist in the mass range that many theorists favor, Darwin should see them. If not, then theorists will have to go back to the drawing board. Candidate 3. Axions. Axions are even stranger than WIMPs. They were not invented to explain dark matter. They were invented to solve a problem in particle physics called the strong CP problem. Let me try to explain without going too deep into quantum chromodynamics. The strong nuclear force, the force that holds protons and neutrons together in the atomic nucleus, has a property called CP symmetry. CP stands for charge conjugation and parity. Basically, swapping particles with their antiparticles and flipping left and right. Most physical laws are CP symmetric. They look the same if you swap matter with antimatter and mirror the world. But the strong force, according to the equations, could violate CP symmetry. It does not. We have measured it, and it doesn't. There is a parameter in the equations called theta that could be non-zero, but experiments show it is zero, or very close to zero. Why? One possible answer: a new particle that cancels out the CP violation. That particle was named the axion, after a brand of laundry detergent, because it cleans up the problem. The axion, if it exists, would be extremely light, maybe 1/1,000,000th of an electron volt, or even less. It would be produced in enormous numbers in the early universe. It would not interact strongly with normal matter. It would behave, in many ways, like dark matter. Experiments like ADMX at the University of Washington use strong magnetic fields, 8 Tesla or more, inside a microwave cavity. If axions exist, they should convert into microwave photons in the presence of a magnetic field. The experiment tunes the cavity, changes its resonant frequency to listen for a signal. No axions yet, but the search continues, and axions remain a viable candidate. Candidate 4. Sterile neutrinos. Ordinary neutrinos are abundant. About 100 trillion neutrinos pass through your body every second, most of them from the sun. But neutrinos are extremely light, lighter than 1/1,000,000th of an electron volt, and they are hot, dark matter, meaning they move at nearly the speed of light. Hot, dark matter would smooth out small-scale structure in the universe. We see small-scale structure, dwarf galaxies, globular clusters. So hot dark matter cannot account for most dark matter, but there is a hypothetical particle called the sterile neutrino. Sterile neutrinos would be heavier than ordinary neutrinos, maybe thousands or millions of times heavier. They would not interact via the weak force, hence sterile, only via gravity and possibly a special mixing with ordinary neutrinos. Sterile neutrinos would be warm dark matter, moving faster than cold dark matter but slower than hot. Warm dark matter would suppress the formation of small galaxies. Observations of small satellite galaxies around the Milky Way suggest that dark matter is not too warm, but they do not rule out sterile neutrinos at certain masses. Future observations from Roman itself, mapping the distribution of small galaxies, could provide a definitive test. Candidate 5. Primordial black holes. What if dark matter is just black holes, but not the black holes formed from dying stars? Primordial black holes could have formed in the first second after the Big Bang, 1 second, when the universe was incredibly dense and density fluctuations were extreme. If a region of space was dense enough, it could have collapsed directly into a black hole without first forming a star. These primordial black holes could have any mass, from tiny pebbles to millions of times the mass of the sun. For decades, primordial black holes were considered a fringe candidate. But in recent years, the discovery of gravitational waves from black hole mergers by LIGO and Virgo has revived interest. LIGO sees black holes that are heavier than expected from stellar collapse, tens of solar masses, rather than 5 to 10. Some of those black holes could be primordial. However, if primordial black holes of a certain mass range were common, LIGO would have seen more mergers than it has. Current constraints say primordial black holes cannot be all of dark matter, but maybe some fraction, maybe 10%, maybe 1%. We do not know. The real answer, we don't know. The honest truth, the truth we will speak softly tonight, is that we do not know. We have ruled out some possibilities. We have narrowed the parameter space. We have set limits. Dark matter cannot be made of ordinary atoms. It cannot be made of machos. It cannot be made of neutrinos. But the nature of 85% of the mass of the universe remains a mystery. That is why Roman matters. Roman will not detect dark matter directly. It does not have the instruments for that. It is a telescope, not a particle detector. But Roman will map the distribution of dark matter with unprecedented precision. Where is dark matter clumpy? Where is it smooth? How has it changed over cosmic time? That map, the dark matter map of the universe, will tell us what dark matter is not. And sometimes, ruling things out is how you find the truth. Dark energy, the accelerating push. Now let us turn from dark matter, the invisible glue that holds galaxies together, to dark energy, the invisible force that is pushing the universe apart. If dark matter was discovered through gravity pulling inward, dark energy was discovered through gravity pushing outward. Or rather, through the discovery that something is counteracting gravity on the largest scales. The unexpected supernovae. The year, 1998. The place, two competing teams, sharing the same goal, unaware that they would end up sharing the Nobel Prize. Team 1, the Supernova Cosmology Project, led by Saul Perlmutter. Perlmutter was a physicist at Lawrence Berkeley National Laboratory in California. He had started the project in the late 1980s, before anyone else. He was methodical, careful, thorough. Team 2, the High-Z Supernova Search Team, led by Brian Schmidt. Schmidt was an Australian astronomer working at the Harvard-Smithsonian Center for Astrophysics in Cambridge, Massachusetts. He started his project later than Perlmutter, but his team was smaller and faster. They made decisions quickly, took risks. Adam Riess was a postdoctoral researcher on Schmidt's team. He was the one who wrote the software to find supernovae in the images. Both teams were looking for Type 1, a supernovae. Let me explain what a Type 1a supernova is. Because it is beautiful, and because understanding it is key to understanding dark energy. The life and death of a Type Ia supernova. A Type 1. A supernova starts with a binary star system, two stars orbiting each other. One of the stars is a white dwarf. A white dwarf is the remnant of a star like our Sun after it has exhausted its nuclear fuel. Our Sun, in about 5 billion years, will swell into a red giant. It will engulf Mercury, Venus, and probably Earth. Then it will shed its outer layers and collapse into a white dwarf. A white dwarf is about the size of Earth, roughly 8,000 miles in diameter, but it contains about half the mass of the Sun. That means it is incredibly dense. A teaspoon of white dwarf material would weigh about 10 tons, about as much as a school bus. In a binary system, the white dwarf can steal gas from its companion star. The gas flows from the companion onto the white dwarf. The white dwarf grows. It becomes more massive. It approaches a critical mass, 1.4 times the mass of the Sun. That number is called the Chandrasekhar limit, named after the Indian astrophysicist Subramanian Chandrasekhar, who calculated it in 1931 when he was just 19 years old. The Chandrasekhar limit is the maximum mass that a white dwarf can have without collapsing. If the white dwarf exceeds that limit, if it pulls in too much gas from its companion, it can no longer support itself. The pressure at its center becomes so high that carbon and oxygen atoms start to fuse, to undergo nuclear fusion. Even though the white dwarf is no longer a star in the normal sense, fusion spreads through the white dwarf in a matter of seconds. In less than a second, less time than it takes you to blink, the white dwarf fuses a significant fraction of its mass into heavier elements: nickel, cobalt, iron. The energy released is enormous. For about 2 weeks, the supernova outshines an entire galaxy, 100 billion stars. Then it fades. The key point for cosmology. Type 1. A supernovae have a very consistent peak brightness. Why? Because they always explode at nearly the same mass, the Chandrasekhar limit. There is some variation, fainter ones, brighter ones, but astronomers have learned to correct for the variation using the stretch of the light curve. How fast the supernova brightens and fades. After correction, type 1. A supernovae are standard candles. They tell you distance. Both teams measured the distances to dozens of type 1a supernovae. They also measured the redshift of each supernova, how much the expansion of the universe had stretched its light. Redshift is measured with spectrographs, the same kind of instrument that Vera Rubin used to measure galaxy rotation, but much more sensitive. From the redshift and the distance, you can determine the expansion history of the universe. Here is the expectation. If the universe's expansion is slowing down due to gravity pulling everything together, then distant supernovae would appear brighter than in a universe with no slowing. Their light would have had less time to spread out, but that is not what they found. The supernovae were fainter than expected, significantly fainter, about 20% fainter for the most distant ones. That means they are farther away than expected by about 20%. That means the universe is not slowing down. It is speeding up. Something is pushing the galaxies apart, not just expanding, but accelerating. The announcement was made in 1998 at a meeting of the American Astronomical Society in January. Perlmutter presented first, then Schmidt. Rias was in the audience. After the talks, the room was silent. People did not know what to say. The results seemed impossible. Astronomers are conservative by nature. They have to be, because the sky is full of surprises, and you do not want to mistake a systematic error for a discovery. But both teams had done their checks. Both teams had considered dust. Dust can make supernovae appear fainter, mimicking acceleration. They had corrected for dust using infrared observations. Dust does not absorb infrared as much as it absorbs visible light. Both teams had considered the possibility that type 1a supernovae were not perfect standard candles at high redshift. Maybe the older universe made different supernovae. They had checked with other distance indicators, with galaxy clusters, with the cosmic microwave background. Everything pointed the same direction. The universe is accelerating. By the early 2000s, the result was confirmed. Perlmutter, Schmidt, and Rias received the Nobel Prize in Physics in 2011. Their citation, for the discovery of the accelerating expansion of the universe through observations of distant supernovae. The simplest explanation for dark energy is the cosmological constant. Albert Einstein added it to his equations of general relativity in 1917. He did it because he believed the universe was static. His equations without the constant predicted that the universe should either expand or contract. That bothered him. It bothered everyone at the time, so he added a term, the cosmological constant, written in equations as the Greek letter lambda. The constant represented a repulsive force that could balance gravity. If you got the value just right, gravity and repulsion would cancel, and the universe would stay still. In 1929, Edwin Hubble discovered that the universe is actually expanding. Einstein did not need the constant anymore. He called it his biggest mistake. But in 1998, it turned out the constant might be needed after all. The cosmological constant, a constant energy density of empty space, produces exactly the kind of accelerating expansion we observe. Space itself has energy. That energy has negative pressure. Negative pressure drives acceleration. The constant is not a mistake. It is a property of the vacuum, except There is a problem, a huge problem, a problem so large that it is called the vacuum catastrophe. When physicists calculate the energy density of the vacuum using quantum field theory, the theory of particles and forces, they get a number that is about 120 orders of magnitude larger than the observed value of the cosmological constant, 120 orders of magnitude. That is 10 to the power of 120, A1 with 120 zeros after it. That is the worst prediction in the history of physics. It means either our quantum field theory is wrong, which is possible, but it works so well in every other context, or there is a cancellation that we do not understand, or the cosmological constant is not the explanation for dark energy. That is why we need Roman. Roman will measure the expansion history of the universe with far greater precision than the supernova teams could in 1998. It will tell us whether dark energy is constant, like the cosmological constant, or whether it changes over time. If it changes, even a little, that would be the biggest discovery in cosmology since the discovery of the expanding universe itself. Alternative possibilities: quintessence, modified gravity, and the void. If dark energy is not constant, what could it be? Quintessence. A dynamical field, like the electromagnetic field, but everywhere, all the time. That changes strength over time. In quintessence models, dark energy was weak in the early universe and became strong only recently, when the universe was about half its current age. That timing, the fact that dark energy started dominating just a few billion years ago, is one of the great puzzles of cosmology. It is called the coincidence problem. Why now? Why not 10 billion years ago? Or 10 billion years from now? Quintessence models offer an explanation. The field was tracking the density of matter, waiting until matter became dilute enough to take over. Modified gravity. What if gravity does not behave exactly as Einstein predicted on cosmological scales? Perhaps there is no dark energy. Perhaps general relativity is incomplete. Theories like F, gravity, where the gravitational action is a function of the Ricci scalar curvature, attempt to modify the equations to produce acceleration without a dark energy field. These theories make different predictions for the growth of structure. In standard dark energy models, structure grows at a certain rate. In modified gravity models, structure might grow faster or slower. Roman will measure the growth of structure through weak lensing and galaxy clusters. If the growth rate does not match the expansion history, that would be evidence for modified gravity, the void model. What if we are just in a giant void, a large underdense region, and the apparent acceleration is an illusion? In a void, the expansion rate could appear faster than it really is, because we are looking outward from a region of lower density. This is a minority view. Most evidence contradicts it. The cosmic microwave background, the afterglow of the Big Bang, looks too uniform for such a large void to exist. But the idea is not completely ruled out. Roman's wide field survey will map the density of the universe over large volumes. If we live in a void, Roman will see it. If we do not, Roman will rule it out. Part 5. How Roman will see the invisible. The technical heart. Now we come to the technical heart of the mission. How does a telescope see something that does not emit light? The answer is indirect. Roman will not see dark matter or dark energy. It will see their effects on normal matter and light. Let me walk you through the three main methods. Weak gravitational lensing, baryon acoustic oscillations, and galaxy cluster counting. Weak gravitational lensing, the cosmic mirage. Weak gravitational lensing is the most powerful tool for mapping dark matter. It is based on a prediction of Einstein's general relativity. Mass bends light. Not because light has mass. Light has no mass. But because mass curves the space through which light travels. Imagine a rubber sheet. If you put a heavy ball on the sheet stretches and forms a dip. If you roll a marble across the sheet near the dip, the marble's path curves. That is what mass does to space-time. Now imagine a distant galaxy, 10 billion light-years away. Between us and that galaxy lies a large cluster of galaxies. The cluster contains stars, gas, dust, and dark matter. The dark matter, though invisible, has mass. That mass curves space-time. The light from the distant galaxy travels through the curved space-time of the cluster. The light bends. By the time it reaches Raman's detector, the galaxy's shape is slightly distorted. It might be stretched in one direction, like a circle becoming an ellipse. It might be sheared, rotated, relative to its true orientation. The distortion is tiny, less than 1%. Raman will measure the shapes of hundreds of millions of galaxies, about 300 million in the high-latitude wide area survey alone. By averaging over many galaxies in a given patch of sky, the statistical signal of lensing emerges. From that signal, astronomers can reconstruct the distribution of dark matter, the invisible skeleton of the cosmos. Where the lensing signal is strong, dark matter density is high. Where the signal is weak, dark matter density is low. The map will have a resolution of about 1 arc-minute, about the size of a nickel seen from a mile away. That is not as sharp as Hubble's images. Hubble can resolve objects 1/10 of that size. But Raman's map will cover 50 times more area. You cannot see the whole forest with a microscope. You need a wide-angle lens. That is Raman. Baryon acoustic oscillations. The standard ruler. There is another way to measure dark energy, independent of supernovae and lensing. It uses sound waves that traveled through the early universe. In the first few 100,000 years after the Big Bang, the universe was a plasma, a hot soup of photons, electrons, and protons. The photons and electrons were tightly coupled. They scattered off each other constantly. Sound waves, compression waves, traveled through this plasma. These sound waves were driven by gravity, which pulled matter together, and pressure, which pushed it apart. The result was a pattern of oscillations. Regions where matter was slightly denser, separated by a characteristic distance. When the universe cooled enough for electrons and protons to combine into neutral hydrogen, about 380,000 years after the Big Bang, the photons stopped scattering. They flew free. That is the cosmic microwave background, the oldest light in the universe. But the sound waves left an imprint. The denser regions, the peaks of the sound waves, had more matter. That extra matter attracted more matter over time. Through gravity, the peaks grew into galaxies and clusters of galaxies. The characteristic separation of the peaks, the sound horizon, is about 500 million light-years today. That is a standard ruler. We know its true length from the cosmic microwave background, measured with exquisite precision by satellites like WMAP and Planck. We measure its apparent length at different epochs in cosmic history by looking at the distribution of galaxies. If dark energy is accelerating the expansion, the apparent length of the standard ruler will change in a specific way. Roman will measure the standard ruler over a volume of the universe that is larger than any previous survey. The precision will be breathtaking. Galaxy clusters, the rare objects. Dark matter pulls galaxies together into clusters. The number of galaxy clusters in the universe depends on both the amount of dark matter and the properties of dark energy. More dark energy, or stronger dark energy, makes it harder for clusters to form. Why? Because dark energy pushes things apart. If you are trying to assemble a cluster to pull together trillions of solar masses of dark matter and gas, you need gravity to overcome the expansion. Dark energy opposes that. So, the number of clusters as a function of their mass and redshift is a sensitive test of dark energy. Roman will find tens of thousands of galaxy clusters, about 20,000, through two methods. First, by their weak lensing signal. Clusters are massive, so they produce strong lensing. Second, by their X-ray emission. The hot gas in clusters glows in X-rays, and Roman will see that glow in its infrared detectors because of a trick. The X-rays heat the gas, which emits infrared radiation indirectly. By counting clusters and measuring their masses, Roman will test dark energy. The power of Roman is not any single method. It is the combination of all three: weak lensing, mapping dark matter, and the growth of structure. Baryon acoustic oscillations, mapping the expansion history. Galaxy clusters, mapping the abundance of rare objects. And on top of that, thousands of Type 1, a supernovae from the High Latitude Time Domain Survey. Each method has its own systematic errors, biases that could mimic a false signal. By combining them, Roman will cross-check itself. If all four methods point to the same dark energy model, we can be confident that the model is correct, or at least that it fits the data. If they disagree, if the lensing says one thing and the supernovae say another, that disagreement itself will be a discovery. It will mean that our understanding is missing something fundamental. That is the best possible outcome, because nothing drives science forward like a good contradiction. Beyond dark matter and dark energy, exoplanets, galaxies, and cosmic time, Roman is not a one-trick pony. While it stares at the dark universe, mapping the invisible skeleton of dark matter and measuring the accelerating push of dark energy, it will also make breathtaking discoveries in other areas. These are what astronomers call ancillary science, the unexpected gifts that come from building a powerful observatory and pointing it at the sky. But the word ancillary is misleading. It makes these discoveries sound like bonuses, like side dishes. Some of them may turn out to be the main course. Let me walk you through them, slowly, because each one is a universe of wonder. Microlensing planets, finding worlds without stars. Most exoplanets, planets orbiting other stars, are discovered by the transit method. A transit happens when a planet passes directly between us and its star. The planet blocks a tiny fraction of the star's light, maybe 1%, maybe much less. And the star dims for a few hours. When the transit ends, the star brightens again. By measuring the depth of the dimming, you can calculate the size of the planet. By measuring the time between transits, you can calculate the planet's orbital period. its year. By applying Kepler's laws, you can calculate the distance from the planet to its star. The transit method is powerful. NASA's Kepler mission used it to discover more than 2,600 confirmed exoplanets, with thousands more candidates waiting to be confirmed. The Transiting Exoplanet Survey Satellite, TESS, is doing the same thing right now, focusing on the brightest stars in the sky. But the transit method has limitations. It only works for planets whose orbits are edge-on from our perspective. If the orbit is tilted, even a little, the planet will never cross the face of the star as seen from Earth. No transit means no detection. The transit method also favors planets close to their star. Close-in planets are more likely to transit, and they transit more often. Hot Jupiters, gas giants orbiting their stars every few days, are the easiest to find. Earth-sized planets in Earth-like orbits. 1 year, not a few days. Transit once a year, and you need at least 3 transits to confirm the planet. That takes 3 years of continuous observation. And the dimming from an Earth-sized planet is tiny, about 1/100th of 1%. That is hard to measure. Roman will use a completely different method, microlensing. I have mentioned microlensing before, in the context of machos. Now let me explain it in detail, because it is one of the most beautiful and counterintuitive phenomena in astronomy. How microlensing works. Microlensing relies on a prediction of general relativity. Mass bends light. If a massive object passes almost exactly in front of a more distant light source, the object's gravity bends the light from the source and focuses it toward the observer. The source appears to brighten. The brightening follows a characteristic curve. It rises slowly at first, then faster, then peaks, then fades. The entire event takes days or weeks, depending on the mass of the lensing object and the relative motions. If the lensing object is a star, which is what happens in most microlensing events, the peak brightening is modest, maybe a factor of 10. But if the lensing object is a star with a planet, the planet adds its own gravitational tug. The planet's gravity changes the magnification pattern slightly, adding a blip to the light curve. That blip lasts for hours, sometimes just a few hours, before the magnification returns to the star-only curve. By measuring the shape, duration, and position of the blip, you can calculate the mass of the planet and its distance from the star. Microlensing is sensitive to planets that no other method can find. First, low-mass planets. The transit method struggles to find planets smaller than Earth. The dimming is too small. The radial velocity method, which measures the wobble of a star as a planet tugs it, also struggles with small planets, especially if they are far from the star. Microlensing can detect planets as small as Mars. Second, distant planets. The transit method is blind to planets beyond about 1 astronomical unit, the distance from Earth to the Sun. The radial velocity method is also biased toward close-in planets. The wobble is larger and easier to measure when the planet is close. Microlensing can detect planets at any distance from their star, from scorching hot close orbits to frozen orbits beyond Neptune. It can even detect planets that have no star at all. Third, free-floating planets. A free-floating planet, sometimes called a rogue planet, is a planet that was ejected from its star system by gravitational interactions. When a planet forms, it does not always stay in its original orbit. The gravity of other planets can fling it outward. If the planet gets too close to a giant planet like Jupiter, it can be ejected entirely, sent flying into the galaxy with no star to orbit. How many free-floating planets are there? Estimates vary wildly. Some astronomers think there are as many free-floating planets as stars, about 100 billion in the Milky Way. Others think there are many more, maybe 10 times as many, maybe 100 times as many. We do not know, because free-floating planets are dark. They emit no light. They are not hot enough to glow. The only way to find them is microlensing. If a free-floating planet passes between us and a distant star, its gravity will magnify the star's light, just like a star does, but with a different time scale. A star produces a microlensing event lasting weeks. A Jupiter-mass free-floating planet produces an event lasting days. An Earth-mass free-floating planet produces an event lasting hours. A Mars-mass free-floating planet produces an event lasting minutes. Roman will stare at the galactic bulge, the crowded center of the Milky Way, for about 70 days per year, taking an image every 15 minutes. It will detect thousands of microlensing events. Most will be caused by stars, ordinary stars in the bulge. But a fraction, maybe a few percent, will be caused by planets. Some of those planets will be bound to stars. Roman will see the star's lensing curve plus the planet's blip. Others will be free-floating. Roman will see the lensing curve alone, with no star to explain it. By counting the number of free-floating microlensing events and their durations, Roman will produce the first accurate census of rogue planets in the Milky Way. That census will tell us how common Earth-mass free-floating planets are. And that number, the number of orphaned worlds wandering the galaxy in eternal darkness, will reshape our understanding of planet formation. Because if free-floating planets are common, then planet ejection is common. And if planet ejection is common, then many star systems, maybe most star systems, lost planets early in their histories. Our own solar system might have lost planets. We do not know. Roman will begin to answer that question. Galaxies across cosmic time. Roman as a cosmic historian. Roman's wide field and infrared sensitivity make it an ideal galaxy survey machine. Let me give you a sense of the scale. Hubble's deepest image, the Hubble Ultra Deep Field, covers an area of the sky about 1/10 the diameter of the Moon. That patch of sky contains about 10,000 galaxies. Each of those galaxies is billions of light years away. Each of those galaxies contains billions of stars. The ultra-deep field is one of the most famous images in the history of astronomy. It changed how we think about the universe, but it is tiny. You could fit the ultra-deep field into the area of the full moon about 100 times. And you could fit the full moon into the area of the entire sky about 200,000 times. The sky is huge. Roman will cover 5,000 square degrees, 1/8 of the entire sky. That is about 50 times the area of all previous Hubble surveys combined. In each of those square degrees, Roman will see galaxies as faint as those in the Hubble ultra-deep field, or nearly so. That means Roman will discover not thousands of distant galaxies, not millions, but hundreds of millions, 300 million galaxies. That is the target number for the High Latitude Wide Area Survey. Each galaxy will have a measured shape for weak lensing. Each galaxy will have a measured distance, or at least a photometric redshift, an estimate of its distance from its colors, which is less precise than a spectroscopic redshift, but good enough for statistical measurements. And each galaxy will be stored in a catalog. A list that astronomers will mine for decades. What will they find? First, rare objects. The rarer something is, the more sky you need to cover to find it. If there is one galaxy of a certain type in every 10 square degrees of the sky, Hubble would never find it. Hubble could only see a few square degrees in its entire lifetime. Roman will see 5,000 square degrees, so Roman will find the rarest objects in the universe. What kinds of rare objects? High redshift quasars, supermassive black holes that were actively feeding when the universe was less than 1 billion years old. We have found a few hundred of these with ground-based telescopes. Roman will find tens of thousands. Each of these quasars is a beacon, a point of light so bright that it outshines its entire host galaxy. By studying the spectrum of that light, astronomers can measure the composition of the intergalactic medium, the thin gas that fills the space between galaxies. That gas contains clues about the epoch of reionization, the period when the first stars and galaxies ionized the neutral hydrogen that filled the early universe. Second, galaxy protoclusters. A protocluster is a galaxy cluster in the process of forming. The galaxies are not yet bound together. They are still falling toward each other, still gathering mass. Protoclusters are the seeds of the structures we see today, the massive clusters that dominate the cosmic web. Roman will find thousands of protoclusters by looking for overdensities of galaxies in its wide-field images. Each protocluster will be studied with follow-up telescopes. Webb, the extremely large telescope, the 30-meter telescope. To understand how galaxies form and evolve in dense environments. Third, ultra-diffuse galaxies. These are ghostly galaxies. They have as many stars as a small galaxy, but spread out over a volume as large as the Milky Way. That means they are incredibly faint. You can see right through them. Ultra-diffuse galaxies are dominated by dark matter. Their stars are just a sprinkling on an invisible ocean. Roman, with its wide field and infrared sensitivity, will find thousands of ultra-diffuse galaxies in the nearby universe. By measuring their total mass through the motions of their stars and comparing it to their visible mass, astronomers will test whether dark matter behaves the same way in these diffuse objects as it does in ordinary galaxies. If it does not, if ultra-diffuse galaxies have a different dark matter distribution, that could be evidence for a new property of dark matter, like self-interaction. Self-interacting dark matter particles that can bump into each other, would produce different structures than collisionless dark matter. Roman might see the difference. Time domain, the changing sky. The universe is not static. This is a fact that is easy to forget because the stars seem fixed. Night after night, the same stars rise in the same places. The constellations, Orion, Ursa Major, Scorpius, look the same to us as they did to our great-grandparents. But that is because we live on human timescales. On cosmic timescales, weeks, years, decades, the sky changes. Stars explode. Supermassive black holes swallow stars and flare up. Magnetars. Neutron stars with magnetic fields, 1,000 trillion times stronger than Earth's release bursts of energy that outshine entire galaxies for milliseconds. Binary stars eclipse each other. Asteroids in our solar system move across the sky. Distant galaxies vary in brightness as their central black holes consume gas. Roman will stare at the same patches of sky repeatedly, dozens or hundreds of times over 5 years. By subtracting one image from another, taking the difference, Roman software will detect everything that changed. This is called a time domain survey. The high-latitude time domain survey will cover about 20 square degrees, a small area by Roman standards, but much larger than any previous time domain survey from space. It will take an image of that area every few days, sometimes every day. For the entire mission, that cadence, the time between images, is optimized for catching supernovae. A Type 1a supernova takes about 20 days to reach peak brightness and another 40 days to fade away. If you take an image every 5 days, you will catch the rise and fall of the light curve. Roman will find more than 10,000. Type 1, a supernovae, a factor of 100 more than the 1998 Discovery teams had. The orbit, stability at L2. Roman will not orbit Earth like Hubble does. Hubble orbits at an altitude of about 540 kilometers, low enough for space shuttle astronauts to reach it for repairs. Roman will go to Sun-Earth Lagrange Point 2, L2. Lagrange points are positions in space where the gravitational forces of two large bodies, in this case, the Sun and the Earth, balance the centrifugal force felt by a smaller body. An object placed at a Lagrange point stays roughly in place relative to the two large bodies, without using much fuel to maintain its position. There are 5 Lagrange points in the Sun-Earth system. Lone is between the Sun and Earth, about 1.5 million kilometers from Earth toward the Sun. The Deep Space Climate Observatory, DSEOVR, is at Lone, monitoring solar wind. L2 is opposite Lone, about 1.5 million kilometers from Earth, in the direction away from the Sun. Data volume, 20 petabytes of discovery. Roman will produce about 20 petabytes of data over its 5-year mission. 20 petabytes is 20 million gigabytes. That is roughly 2,000 times the entire text content of the United States Library of Congress. Every hour. How does Roman produce so much data? Each image from the Wide Field Instrument is about 300 million pixels. 300 megapixels. At 16 bits per pixel, that is about 600 megabytes per image. Roman will take hundreds of images per day, thousands per week. Over 5 years, the data will be downlinked to Earth twice per day via the Deep Space Network, a global network of giant radio dishes in California, Spain, and Australia. The downlink rate is about 250 megabits per second, about the speed of a good home fiber internet connection. Each downlink pass will take about 8 hours. By the end of the mission, the total data volume will exceed 20 petabytes. That data will be processed at the Space Telescope Science Institute in Baltimore, the same institution that processes Hubble and Webb data. The data will be calibrated, corrected for instrumental effects, combined into mosaics, measured for shapes and brightnesses. Then the data will be released to the world. No proprietary period, no hidden data. As soon as Roman observes, the data become public. Anyone, any student, any amateur, any curious human, can download Roman data and make discoveries. That is NASA's policy. Open data, open science. It is a gift to the world. The future of cosmic observation extends far beyond the current decade. While the Roman Space Telescope will serve as our primary eye into the early 2030s, a new generation of observatories is already being conceptualized. The top priority for the next era is the Habitable Worlds Observatory, or HWO. This ambitious mission is designed for two profound goals: the direct imaging and atmospheric analysis of Earth-like planets orbiting distant suns. To achieve this, the HWO will require a contrast ratio 10 times more precise than current technology, utilizing advanced light-masking systems or external star shades to reveal the subtle chemical signatures of oxygen, methane, and water vapor, the potential fingerprints of life across the stellar gap. Working alongside these visual giants will be the Origin Space Telescope, designed to operate in the far infrared spectrum at temperatures near absolute zero. This observatory will peer into the cold, dusty cradles where planets are born. By mapping the distribution of water and organic elements in young solar systems, it will help us understand the origins of Earth's own oceans. Meanwhile, the era of gravitational wave astronomy will reach new heights with LISA, a space-based interferometer consisting of 3 spacecraft separated by millions of kilometers. By measuring the subtle ripples in the fabric of space-time caused by the union of supermassive black holes, LISA will provide a symphony of data that complements the visual surveys of Roman, painting a complete picture of the universe's most energetic events. This journey of exploration reaches its climax on a quiet night in Florida. Imagine the scene at Cape Canaveral. A towering launch vehicle stands ready on the pad, its white exterior illuminated by bright floodlights. Encased within the protective fairing at the summit sits Roman, the silent passenger prepared for its million-mile voyage. As the countdown reaches its final moments, the systems transition to autonomous control. At the moment of departure, a massive release of energy propels the vehicle upward, clearing the tower and beginning a graceful arc toward the eastern horizon. The deep, rhythmic vibration of the ascent can be felt for miles, a testament to the engineering required to reach the stars. Minutes into the flight, the primary stages complete their task and separate, allowing the upper stage to carry the telescope into the vacuum. The protective fairing opens like a shell, exposing Roman to the stillness of space for the very first time. Following a precise orbital maneuver, the telescope is set on its trajectory toward the second Lagrange point. There, far from the interference of Earth's atmosphere, it will begin its mission. This is more than a technical achievement. It is a promise for the future. From the stable environment of the stasis pod to the vast lenses of the next generation of telescopes, humanity continues its steady, rhythmic march into the unknown, seeking to answer the simplest and most profound question of all. Are we alone among the stars? The cruise. 30 days of deployment. Roman will take about 30 days to reach L2. During that time, it will unfold. The solar arrays, 2 large panels, will deploy first. They are Roman's power source, converting sunlight into electricity. The high-gain antenna, a small dish, will deploy next. That is Roman's communication link to Earth. The sun shield, a set of lightweight reflective blankets, will deploy. The sun shield is not as complex as Webb's. Roman is not a far infrared telescope, so it does not need the same level of cooling, but it still needs to keep the telescope in the shade. Without the sun shield, the sun's heat would warm the mirror and the detectors, creating infrared glow that would ruin the observations. The instruments will turn on, one by one. They will be tested. The detectors will be cooled. The coronagraph will run its first sequences, moving its deformable mirrors, blocking a bright star, searching for a planet. The wide field instrument will take its first images, calibration images, not science images, to measure the response of each pixel, to map the flat field, to check the focus, and then first light. First light is the moment when the telescope takes its first science image, a real image of a real patch of sky, intended for real science. For Hubble, first light was a disaster. The blurry image of a star that should have been sharp. For Webb, first light was a triumph, a sharp image of a star called HD 84444. The first light image that Webb's team called a beautiful, sharp crescent of light. For Roman, first light will be something else. It will not be a discovery. It will be a test, a known star field, something boring to the public. The image will be released on NASA's website. A few thousand people will look at it. Most will see a field of dots and say, "That's nice." But to the engineers who built Roman, to the scientists who dreamed of this mission for decades, first light will be a miracle, because they remember when Roman was just a drawing, when it was just a proposal, a few pages of text, a few diagrams, when it was nearly canceled, budget cuts, shifting priorities, the relentless competition for resources, when the mirror was ground and polished, 2.4 meters of perfect glass, and they stood in the clean room and stared at it, wondering if they would ever see it fly. And now it is up there, L2, 1.5 million kilometers from Earth, clicking, counting photons, listening. The Silent Architect, a meditation on dark matter. Let us pause now. Let the science recede for a moment. Let the facts, the dates, the names, the numbers, dissolve like morning mist, and let us sit with the mystery itself. Dark matter, the silent architect. We have never seen it. We have never touched it. We have never made it in a laboratory, but we know it is there. We know it because the stars at the edge of galaxies move too fast. We know it because the light from distant galaxies is bent, stretched and sheared by a mass we cannot see. We know it because without it, the universe would not look the way it does. There would be no galaxies, no clusters, no cosmic web, no stars, no planets, no life, no us. Dark matter is the foundation upon which everything we know is built, and we do not know what it is. That is a strange thing to say. Imagine building a house on a foundation, a solid, concrete foundation, and then realizing that you have no idea what the foundation is made of. You know it is strong, you know it is stable, you know it holds the house up, but you cannot see it, you cannot touch it, you cannot even name it. That is where we stand. That is the human condition at the beginning of the 21st century. We have mapped the universe, we have measured its expansion, we have photographed its infant glow, the cosmic microwave background, imprinted on the sky when the universe was just 380,000 years old. We have sent probes to every planet in the solar system. We have landed on a comet. We have touched the surface of an asteroid. We have heard the ripples of colliding black holes, gravitational waves that traveled more than 1 billion years to reach us. And yet, 95% of the universe is a mystery. That is not a failure. That is an invitation. Think of the cave painters at Lascaux. They painted the Pleiades on their walls. They did not know what the Pleiades were. They did not know that the Pleiades are a cluster of stars 444 light years away. They did not know that light takes 444 years to travel from those stars to their eyes. They did not know that the stars are nuclear furnaces, fusing hydrogen into helium, releasing energy, shining. They did not know any of that, but they looked, they recorded, they passed their knowledge, their observations, their patterns, their wonder, to their children, and their children's 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 children, after thousands of generations, built telescopes. They built telescopes that could see the Pleiades as individual stars, then as points of light with spectra, then as points of light whose spectra revealed their composition: hydrogen, helium, carbon, oxygen, iron. Then, as points of light whose parallax, their apparent shift as Earth orbited the Sun, revealed their distance, 444 light-years. The cave painters did not know that number, but they started the chain. Every chain of discovery has a first link. Every chain of discovery has a moment when someone, a single human, in a single place, at a single time, decided to look and remember. The cave painters at Lascaux, the stone builders at Nabta Playa, the scribes in Babylon, the court astronomers in ancient China, the Venus watchers in the Maya cities, Galileo with his tube, Herschel with his sweeps, Hubble with his Cepheids, Roman with her vision of a telescope in space, and you, lying on your bed, in your room, on your small planet, are part of that chain. You are the current link. You are the one who is listening to this story. You are the one who will remember. Not all the details, not all the dates, not all the names, but the feeling that there is more than we know, more than we can know, not forever, but now. There is more than we know now, and we will find it. Not you, perhaps, not me, but someone who is not yet born, who is growing in a womb somewhere, who will learn to read and count and ask questions. That someone will look at Roman's data, or at the data from the telescope that comes after Roman, or the one after that, and they will see something, a pattern, a discrepancy, a surprise, and they will say, "That's strange." And that strangeness, that moment of confusion, of wonder, of not knowing, will be the birth of a new understanding. That is how science works. That is how knowledge grows. One strange thing at a time, one question at a time, one human, looking up, refusing to stop wondering. Think of the cave painters at Lascaux. They painted the Pleiades on their walls. They did not know what the Pleiades were. They did not know that the Pleiades are a cluster of stars 444 light-years away. They did not know that light takes 444 years to travel from those stars to their eyes. They did not know that the stars are nuclear furnaces, fusing hydrogen into helium, releasing energy, shining. They did not know any of that, but they looked, they recorded, they passed their knowledge, their observations, their patterns, their wonder, to their children, and their children's 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 children, after thousands of generations, built telescopes. They built telescopes that could see the Pleiades as individual stars, then as points of light with spectra, then as points of light whose spectra revealed their composition: hydrogen, helium, carbon, oxygen, iron. Then, as points of light whose parallax, their apparent shift as Earth orbited the Sun, revealed their distance, 444 light-years. The cave painters did not know that number, but they started the chain. Every chain of discovery has a first link. Every chain of discovery has a moment when someone, a single human, in a single place, at a single time, decided to look and remember. The cave painters at Lascaux, the stone builders at Nabta Playa, the scribes in Babylon, the court astronomers in ancient China, the Venus watchers in the Maya cities, Galileo with his tube, Herschel with his sweeps, Hubble with his Cepheids, Roman with her vision of a telescope in space, and you, lying on your bed, in your room, on your small planet, are part of that chain. You are the current link. You are the one who is listening to this story. You are the one who will remember. Not all the details, not all the dates, not all the names, but the feeling that there is more than we know, more than we can know, not forever, but now. There is more than we know now, and we will find it. Not you, perhaps, not me, but someone who is not yet born, who is growing in a womb somewhere, who will learn to read and count and ask questions. That someone will look at Roman's data, or at the data from the telescope that comes after Roman, or the one after that, and they will see something, a pattern, a discrepancy, a surprise, and they will say, "That's strange." And that strangeness, that moment of confusion, of wonder, of not knowing, will be the birth of a new understanding. That is how science works. That is how knowledge grows. One strange thing at a time, one question at a time, one human, looking up, refusing to stop wondering, the blind spots, what we still cannot see, even with Roman, even with Webb, even with all the telescopes we have today, and all the telescopes we can imagine building in the next 50 years. There will be blind spots. There will always be blind spots, because the universe is larger than our instruments, because the universe is more complex than our theories, because the universe does not care what we want to know. It will keep its secrets, but we can learn to ask better questions. Let me name some of the blind spots, the questions we cannot yet answer, the phenomena we cannot yet see. Naming them is the first step. The cosmic dark ages, before the first stars. We have seen the cosmic microwave background, the afterglow of the Big Bang. We have seen the first galaxies, the ones that formed when the universe was about 300 million years old. But the period in between, from about 380,000 years after the Big Bang to about 100 million years, is called the cosmic dark ages. No stars, no galaxies, no light, only neutral hydrogen, atoms of hydrogen, each with one proton and one electron, drifting through the expanding universe. The neutral hydrogen emits and absorbs light at a very specific wavelength, 21 centimeters. That 21 centimeter line is in the radio part of the spectrum, but the expansion of the universe has stretched that 21 centimeter line to longer and longer wavelengths. At the beginning of the Dark Ages, when the universe was 380,000 years old, the 21 centimeter line has been stretched to about 1 meter. By the end of the Dark Ages, when the first stars were forming, the 21 centimeter line has been stretched to tens of meters. To see the Dark Ages, we need a radio telescope that can detect signals at wavelengths of 1 to 100 meters. That means a telescope in space. Because Earth's atmosphere reflects or absorbs most radio waves at those wavelengths. Specifically, we need a telescope on the far side of the moon. The moon's far side is permanently shielded from Earth's radio noise. No FM radio, no Wi-Fi, no cell phones, no radar, no television, just the quiet hum of the universe. Several concepts exist for a lunar radio telescope. One concept: land a small satellite in a crater on the far side. A satellite with simple dipole antennas, like rabbit ears. Another concept: stretch a wire mesh across a large crater, 1 kilometer across, and suspend a receiver above it. That telescope would be enormous, far larger than anything we could launch from Earth, and it would see the Dark Ages. It would map the neutral hydrogen as it slowly clumped together, pulled by gravity, forming the first structures. Those structures would eventually become the seeds of the first stars. We have never seen that process. We do not know how the first stars formed. We do not know whether they formed in isolation or in clusters. We do not know how massive they were. The Lunar Radio Telescope, if built, would answer these questions. It is not funded, it is not scheduled, but it is possible. It is within our engineering capability. We just need to decide to do it. The first stars, population 3. The first stars, the ones that ended the Dark Ages, are called population 3. They are called population 3 because astronomers classify stars into populations based on their composition. Population 1, stars like our Sun, are rich in heavy elements heavier than hydrogen and helium. Population 2, older stars, have fewer heavy elements. Population 3, the very first stars, should have no heavy elements at all, only hydrogen and helium, because the universe did not have any heavy elements until the first stars created them through nuclear fusion and scattered them in supernova explosions. Population 3 stars would have been enormous, hundreds of times the mass of the Sun. Why so large? Because without heavy elements, gas could not cool efficiently. The gas that collapsed to form the first stars was hot, thousands of degrees, and it stayed hot. Hot gas has high pressure. High pressure resists gravity. To overcome gravity, you need a lot of mass. So the first stars were massive. They lived fast, only a few million years, because massive stars burn their fuel at a prodigious rate. They died young, exploding as supernovae or collapsing directly into black holes. We have never seen a population 3 star. Webb has searched in its deepest images, in the most distant galaxies. It has found candidates. Galaxies with very little heavy element abundance. Spectra that look different from any known galaxy, but no definitive detection. Why are they so hard to find? Because they are extremely far away. Their light has been traveling for more than 13 billion years, because they are embedded in dusty galaxies. The dust blocks visible light, though infrared can see through, because they are short-lived. By the time we look, many of them have already exploded, and because they are rare, there were far fewer stars in the early universe than there are today. Roman will help. Roman's wide-field surveys will cover large areas, 5,000 square degrees, increasing the chance of catching a population 3 galaxy in the act. If Roman finds a candidate, an extremely distant galaxy with an unusual spectrum, Webb will follow up. Together, they might finally see the first stars. Exoplanet surfaces, the missing image. We have detected thousands of exoplanets. We have measured the composition of some of their atmospheres. We have mapped the temperature of others, hot spots and cold spots as they rotate. But we have never seen the surface of an exoplanet. We have not seen a continent. We have not seen an ocean. We have not seen a cloud. We have not seen a polar ice cap. We have not seen a desert. We have not seen a forest, or the alien equivalent of a forest. All we have, for even the closest exoplanets, is a single dot of light. That dot of light contains information, its brightness, its color, how it changes as the planet rotates and orbits. From that information, we can infer continents and oceans by watching how the reflected light changes as the planet turns. From the light curve, the brightness versus time, we can sometimes infer the presence of large surface features. but we cannot see them. To see the surface of an exoplanet, to resolve it as a disk, not a dot, we need an interferometer. An interferometer with telescopes separated by kilometers, or tens of kilometers, or hundreds of kilometers. The resolution of an interferometer is roughly the wavelength of light divided by the separation between the telescopes. For visible light, wavelength about 500 nanometers, and separation of 1 kilometer. That is enough to see a continent on an exoplanet at 10 light-years away. The technology is hard, but not impossible. The European Space Agency has a concept called LIFE, the Large Interferometer for Exoplanets. NASA has studied similar concepts. The Exoplanet Direct Imaging Mission, neither is funded, neither is scheduled, but someday, maybe in the 2040s, maybe later, someone will launch an interferometer, and the first image of an exoplanet's surface, a blurry, low-resolution image of a world orbiting another star, will be the most famous picture in human history, because it will answer the question that the cave painters asked, that the Babylonians asked, that Galileo asked, that Nancy Grace Roman asked when she was 4 years old. Are we alone? Primordial gravitational waves. The first trillionth of a second. The cosmic microwave background, the afterglow of the Big Bang, is almost perfectly uniform. Almost. There are tiny temperature variations, 1 part in 100,000, caused by acoustic waves in the early universe. Those temperature variations are the seeds of galaxies, the slightly denser regions that eventually collapsed to form the structure we see today. But there is another signal, a more subtle signal, encoded in the cosmic microwave background. It is called B-mode polarization. Polarization is the direction in which light waves oscillate. Most light is unpolarized. Its waves oscillate in all directions. But when light scatters off something, off electrons, off dust, off gas, it can become polarized. The cosmic microwave background was polarized by the scattering of photons off electrons in the early universe. Most of that polarization is E-mode, a curl-free pattern. But B-mode polarization, a curly pattern, can only be produced by 2 things. 1. Gravitational lensing of the E-mode polarization by dark matter. That B-mode signal is small, but we have detected it. 2. Primordial gravitational waves. Gravitational waves produced in the first trillionth of a second after the Big Bang. Those primordial gravitational waves would have stretched and squeezed space, creating a unique B-mode pattern. If we detect that B-mode pattern, we will have direct evidence for cosmic inflation, the theory that the universe underwent a brief period of exponential expansion, a fraction of a second after the Big Bang. Inflation explains many features of the universe. Why it is flat, why it is uniform, why there are temperature fluctuations. But inflation is not yet proven. The B-mode signal from primordial gravitational waves is tiny, much smaller than the B-mode signal from gravitational lensing. To see it, we need a telescope that is extremely cold, extremely sensitive, and extremely clean. Clean, meaning free from contamination by dust. Dust in our own galaxy emits polarized light. That polarized light can mimic the B-mode signal from primordial gravitational waves. The best place to observe the B-mode signal is from space, above Earth's atmosphere, and at frequencies where galactic dust is dim. Several missions have been proposed. Lightbird from Japan, Pico from NASA. None has been fully funded, but the search continues, because detecting primordial gravitational waves would tell us about the very first moments of the universe, the moments before the hot Big Bang, the moments when quantum gravity was the only force that mattered. That is the deepest mystery of all, and someday, perhaps in the 2030s, perhaps later, we will have an answer. Life itself, the biosignature question, the biggest question, the one that sits at the center of everything, is whether we are alone, not whether there are bacteria on Mars, though that would be important, not whether there are microbes in the oceans of Europa, though that would be profound, not whether there are fossils on Enceladus, though that would change everything, but whether there is life elsewhere in the universe that is complex, intelligent, aware, life that builds telescopes, life that wonders about the stars, life that asks, are we alone? We do not know. We have no evidence one way or the other. We have no contact. We have no signal. We have no artifact. We have no proof. But we have a method. We can search for biosignatures. A biosignature is a signal that suggests the presence of life. In astronomy, the most promising biosignature is the combination of gases in an exoplanet's atmosphere. On Earth, life produces oxygen. Lots of oxygen. About 21% of our atmosphere. Oxygen is reactive. It wants to combine with other elements. So, without a constant source, life is that source. But oxygen can also be produced abiotically, by photochemistry in a planet's upper atmosphere. So oxygen alone is not a definitive biosignature. Methane is another possible biosignature. On Earth, methane is produced mostly by life, by cows, by bacteria, by decaying plants. But methane can also be produced by geological processes, by volcanoes, by hydrothermal vents. The combination of oxygen and methane together, that is a strong biosignature. Because oxygen and methane react with each other, they should not coexist in a stable atmosphere. If you see both, something is producing them, and that something is likely life. Water vapor, essential for life as we know it, is also a good sign. But water vapor alone is not enough. Many planets have water vapor without life. The Habitable Worlds Observatory, the telescope that will follow Roman, is designed to directly image Earth-like planets and take spectra of their atmospheres. It will look for oxygen, methane, water vapor, carbon dioxide, and for combinations that are hard to explain without life. If it finds a planet with oxygen and methane together, that will be a discovery. If it finds a planet with seasonal variations in gas composition, maybe green in spring, brown in autumn, that would be even stronger evidence. And if it finds a planet with something unexpected, a gas that we do not produce on Earth, a marker of alien biochemistry, that would be the greatest discovery in human history. The Habitable Worlds Observatory is not funded. It is a dream, but Roman's coronagraph is a step. Roman will test the technology, the coronagraph, the deformable mirrors, the wavefront control that the Habitable Worlds Observatory needs. Roman is the pathfinder for the telescope that may answer the oldest question, the human meaning, why we build. You might wonder, lying there in the dark, listening to this voice. Why does this matter? Why do we spend billions of dollars on telescopes? Why do we send machines to L2? Why do we care about dark matter and dark energy and exoplanets? Why not spend the money on hospitals, on schools, on feeding the hungry? It is a fair question. It is the right question. Let me answer it as honestly and as gently as I can. First, every dollar spent on Roman is spent on Earth. The engineers, the men and women who designed the telescope, they live on Earth. The machinists who ground the mirror, who built the detectors, they live on Earth. The software developers who wrote the code that will process the data, they live on Earth. The administrative assistants who scheduled the meetings, who processed the paperwork, they live on Earth. The janitors who swept the clean rooms, who emptied the trash, they live on Earth. All of them pay taxes. All of them buy groceries. All of them send their children to school. The money is not launched into space. The money circulates through the economy. It creates jobs. It creates skills. It creates knowledge. Second, curiosity is not a luxury. Curiosity is a survival trait. The humans who looked up and wondered what those lights were, they built calendars. Calendars let them plant at the right time. Planting at the right time let them survive winters. The humans who wondered why some stars moved differently, they developed mathematics. Mathematics led to navigation. Navigation led to the crossing of oceans, the sharing of crops, the exchange of ideas. The humans who wondered what the universe is made of, they discovered that the same laws that govern falling apples govern falling planets. Those laws gave us satellites, GPS, the ability to predict hurricanes, to track climate change, to communicate across continents. The humans who wonder now about dark matter, about dark energy, about planets around other stars, they are not wasting time. They are sharpening the human mind. They are training the next generation of problem solvers. The same skills you need to detect a dark matter signal. Statistics, data analysis, pattern recognition, critical thinking are the skills you need to design a vaccine, to model a financial crisis, to understand a changing climate. The same instruments you build to see a galaxy 13 billion light years away, detectors, telescopes, spectrographs, can be turned around to see a cancerous tumor, to image a brain, to monitor a forest. Basic research with no immediate practical application, is the seed corn of applied research. You cannot predict where it will lead. That is why you do it. Third, we need to know. We just do. We need to know what the universe is made of. We need to know where we came from. We need to know whether we are alone. These are not practical needs. They do not put food on the table. They do not keep us warm at night, but they are needs nonetheless. They are needs of the spirit. They are needs of the mind. They are needs of a species that has looked up at the stars for tens of thousands of years and asked, what are they? Why are they there? What is our place among them? You cannot answer that question with a hospital. You cannot answer that question with a school. You need a telescope. You need a telescope like Roman. Nancy Grace Roman understood that. She fought for Hubble not because she wanted to learn something specific, though she did, but because she believed that humanity deserves to know. She believed that knowledge is a good in itself. She believed that the universe is beautiful, not just useful, and that beauty is worth pursuing. She was right. The sound of data, a listening meditation. Let me give you a different kind of image now. Not a picture, A sound. Roman will not actually produce sound. Space is silent. There is no air to carry vibrations, no medium for sound waves. But Roman's data, those 20 petabytes, can be translated into audio. This is called sonification, the process of converting data into sound. Each photon that hits Roman's detector has a wavelength, a color, short wavelength, blue, ultraviolet, high energy, long wavelength. Lower energy. In sonification, we map wavelength to pitch. Short wavelength, high pitch. Long wavelength, low pitch. The brightness of the photon. How many photons arrive per second? Maps to loudness. Bright objects, loud. Faint objects, soft. Now imagine you are sitting at Roman's data stream. Not the raw data, that would be chaos, but a processed version, a sonification designed for listening. You hear a low hum. That hum is the cosmic microwave background, the afterglow of the Big Bang, stretched by the expansion of the universe to microwave wavelengths. It is the quietest sound in the universe, a whisper, a breath, a sigh, but it is everywhere. Every direction you point, Roman, that hum is there. As Roman scans across the sky, the hum changes, slightly. In one direction, toward the constellation Hydra, the hum is slightly warmer, slightly higher in pitch. In the opposite direction, toward the constellation Leo, the hum is slightly cooler, slightly lower in pitch. That is the dipole, the motion of our solar system through the universe. We are moving at about 370 kilometers per second, relative to the cosmic microwave background. That motion shifts the background radiation. Blue shifts it in the direction we are moving. Red shifts it behind us. The hum tells us that, then, a new sound, a sharp ping, like a bell. A single high note, that is a photon, just one. From a galaxy far, far away. The ping is high because the photon is ultraviolet, short wavelength, extremely high energy. It came from a quasar, a supermassive black hole swallowing gas, heating it to millions of degrees. That quasar died long ago. The light has been traveling for more than 10 billion years. But Roman just caught it. Ping. Another ping. Lower this time. A deeper tone. A different galaxy. And another. And another. Over time, the pings merge into a continuous sound. Not a hum, but a murmur. The murmur of galaxies. Hundreds of millions of galaxies. Each one, a slightly different pitch. A slightly different loudness. The murmur rises and falls as Roman scans across the sky. In some directions, toward the galactic plane, the murmur becomes a roar. That is the Milky Way, our own galaxy. Billions of stars, each one a distinct ping, but so many that they blur together into a wall of sound. In other directions, away from the galactic plane, the murmur fades. The sound becomes thin, sparse, like rain falling on a metal roof. Those are the distant galaxies, the ones beyond our own. Then, underneath the murmur, a deeper sound, a thrum, a heartbeat, slow, irregular, faint. That thrum is dark matter, not because dark matter makes sound. It does not, but because the weak lensing signal, The stretching and shearing of galaxy images has a statistical pattern. When you convert that pattern into sound, when you map the lensing shear to a sound wave, you get a pulse. A pulse that repeats every few seconds. Not because dark matter is pulsing, but because the lensing signal has a characteristic scale. That pulse is the silent architect, the invisible skeleton of the cosmos, beating softly. Under everything, you listen. You listen for a long time. The murmur of galaxies, the ping of distant photons, the hum of the cosmic microwave background, the heartbeat of dark matter, and then silence. Not empty silence, full silence. Silence that contains everything. Silence that is the background against which all sounds exist. That silence is the universe before light, before stars, before galaxies, before us, the universe as it was, and as it will be again. When the last star dies, and the last black hole evaporates, and nothing remains but cold, dark, silent space. But that is billions of years from now. Right now, at this moment, there is sound, there is murmur, there is pulse, there is ping, and you, lying in your bed, listening to this voice, are part of it. You are not separate from the universe. You are made of the same atoms that were forged in the hearts of stars. You are the universe's way of experiencing itself. That is not poetry. That is physics. The carbon in your cells was made by fusion in a star. The oxygen in your lungs was made by fusion in a different star. The iron in your blood was made in the final moments of a massive star's life, during the supernova explosion that scattered those atoms across the galaxy. You are star stuff. You are cosmic debris. You are a temporary arrangement of atoms that has, for a brief moment, become aware. And that awareness, that ability to listen to the heartbeat of dark matter, to wonder at the silence beneath the sound, is the universe's gift to itself. So listen. Listen to the murmur. Listen to the pulse. Listen to the silence. And know that you belong here. The end of the mission. A quiet farewell. All missions end. Roman will operate for 5 years. Perhaps 6. Perhaps 7. If the fuel lasts longer than expected and the instruments remain healthy. But eventually, maybe in 2032, maybe in 2033, Roman will take its last image. The image might be of something important. A supernova at the edge of the universe. A galaxy never seen before. Or the image might be of something mundane. A calibration field. A star with a known brightness, used to check Roman's focus. We do not know, but after that last image, Roman will stop responding. The fuel that keeps it pointed at the sky will run out. Without fuel, the reaction wheels will eventually saturate, unable to dump momentum, and Roman will drift. It will drift away from L2. It will enter a chaotic orbit, not around Earth, not around the sun, but a wandering path through the inner solar system. No one will retrieve it. No one will repair it. Roman is not like Hubble. It was not designed for servicing. It was designed for 5 years of flawless operation. And then, silence. We know that. We accept that. But still, when the last signal comes, when the last bit of data is downlinked, when the last command is sent, someone will be listening. Someone at the Space Telescope Science Institute in Baltimore. Someone at NASA's Goddard Space Flight Center. Someone who has worked on Roman for 10 years, 15 years, 20 years. They will watch the signal fade. They will see the telemetry, the temperature readings, the voltage readings, the pointing information. become erratic. They will send a command, a final command, to turn off the transmitter. And then, nothing. The silence will be complete. Roman will become a piece of space junk, a derelict spacecraft, drifting through the void. But Roman will not be dead. It will be sleeping. Its data will live on. 20 petabytes, 20 million gigabytes of images, spectra, light curves. Those data will be stored on servers, on spinning hard drives, on solid-state drives, on magnetic tape, in archives. The data will be copied. They will be backed up. They will be migrated to new storage media as the old media degrades. For decades, for centuries, as long as human civilization survives, Roman's data will be there. Graduate students will download them. Professors will analyze them. Amateur astronomers will explore them. And someday, perhaps 100 years from now, perhaps 1,000, someone will look at a patch of Roman data that no one has ever looked at before, and they will see something strange, something unexpected, something that does not fit, and they will say, "That's interesting," and they will follow it, and they will discover something that we, the people who built Roman, could not have imagined. That is the true legacy of Roman, not the discoveries it makes in its 5-year mission, but the discoveries it enables. In the decades and centuries that follow, Roman is not an end. Roman is a beginning. Epilogue. A bedtime story for Stardust. You are almost asleep now. I can feel it in the rhythm of your breathing. Slower, deeper, more regular. Your eyelids are heavy. Your limbs are heavy. Your mind is soft, like clay that has not yet been fired, ready to hold any shape. Let me leave you with this. The Roman Space Telescope will launch soon, in months, or perhaps a year, depending on the final tests, the weather, the alignment of the planets. But for you, in this room, on this night, Roman has already launched. It is already in your mind. It is already orbiting the darkness between your ears. You have walked from cave paintings to quantum fields. You have traveled from the first human who noticed the Pleiades to the last image Roman will take. You have touched the edge of what is known and peered into the dark beyond. And that dark is not empty. It is full of something we cannot name, something that bends light, something that accelerates expansion, something that holds clusters together, something that is silent, but not absent. We call it dark matter and dark energy because we do not know what it is. Those names are confessions of ignorance, but they are also promises. Promises that we will keep looking, promises that we will keep asking, promises that we will keep building. Better detectors, sharper telescopes, more sensitive instruments, until the dark begins to yield its secrets. The cave painters did not know what the Pleiades were, but they looked. The Babylonians did not know why planets move the way they do, but they recorded. Galileo did not know that his telescope would lead to general relativity, but he pointed it at the moon. Vera Rubin did not know that her flat rotation curves would lead to the discovery of dark matter, but she kept measuring. Nancy Grace Roman did not know that the telescope she fought for would be named after her, but she never stopped fighting. And you, lying in your bed, listening to this voice, you do not know what Roman will discover. No one does. That is the beauty of it. The unknown is not a void. The unknown is a garden, and we are just beginning to walk through it. So sleep now. Sleep deeply. Let the dark hold you. Let the silence wrap around you like a blanket. And when you wake, in the morning, or whenever your eyes open, remember, the universe is made mostly of darkness, but darkness is not empty. It is full of questions, and You are the part of the universe that asks, "Good night, traveler. Good night, stardust. Good night."